sono molto fiduciosi che funzioni tutto. Voi mi sentite, vero?
Sì, sì,
Sì,
sì,
sì, ti
sì.
sei sempre bene, Simonetta.
No, 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 per capire perché a
Forse
volte,
non si sa mai.
sì, no, a volte su questo computer ho avuto dei problemi a volte.
Io spero che si presentino, perché sono veramente tanti.
Perché se no
Sono i primi tre
Appunto, poi sui primi tre, fino alle tre praticamente.
sono i primi tre
e l'ultima.
e l'ultimo. Beh, ora mi sembra strano, insomma, Sarabandi, questa gente che
Comunque, tra l'altro, vedo che da ora siamo anche live su YouTube, quindi magari da controllare che qualcuno si colleghi su YouTube erroneamente, involontariamente. Magari do un controllo. Comunque è bellino lo sfondo che hai dietro. L'hai fa- l'hai
un-
fa- l'hai fatto te di persona quella foto?
Dice a
no,
me?
Sì, esatto.
Sì, l'ho scattata dall'elicottero in Antartide.
Esatto, in
bellino,
Antartide.
bellino, sì.
Ma poi rende, cioè, se la stampi, diciamo, non rende granché, ma così rende perché ha diversi colori molto sfumati, c'è parecchio contrasto, è bellina.
Sì, sembra proprio un poster, vero?
Pensa, non si vede neanche il riflesso del vetro perché l'ho scattata attraverso il vetro.
Ma l'hai scattata te veramente? Io pensavo, cioè, era una battuta la mia, io pensavo che era veramente tipo un'immagine di quelle
No, no,
prestabilite.
no. Qui non c'ho da chiedere copyright,
Quindi
qui tranquillo.
hai anche un lato da fotografo.
Sì. Forse aspetta, ora provo a scrivere una mail a Kimmo e a Anna Contu per ricordargli che ci hanno da presentare.
Almeno loro due. Poi c'è anche tutto il gruppo degli
Perlomeno,
svizzeri.
perlomeno ci sa. Ah no, esatto. Poi c'è Schwank, che però
Anche
perlomeno
non
se ci
abbiamo
fosse
visto
il
nemmeno la
primo.
presentazione.
Aspetta, eh.
E poi io volevo andare a sentire la keynote, tra l'altro.
Beh, insomma, te vai Simonetta, tanto insomma
Ah,
rimaniamo
vabbè,
qua.
sì, ma era la curiosità
Cioè, rimani
di
tu, io e
capire.
Francesco rimaniamo qui per questo. Più che altro io, ecco, sicuramente.
Era la curiosità di capire come mai non si collegava nessuno, ecco. Dopo che si era detto che
Ma secondo me tra 2 minuti o si connettono tutti alle 14:29. In room 1 Francesco non ci sono? Magari si fossero connessi di Laura. Aspetta, c'è l'audio chiuso. Vai, parla
L'ho
ora.
guardato 10 minuti fa.
Ok. Kim Ratianen is online.
Hello.
There?
Hello, Kimmo.
Hello. So again, I wasn't able to get my last name there. Can you see only my first name?
Kimmo.
Hello, Francesco.
I was writing you.
Ah,
Hi, Kim.
Anna, do you know if Anna know about it or to tell you?
yes. Yes, she should know.
Okay.
Have you not received her slides?
Yeah, we have it.
So, but the idea is that I will share my screen.
Yeah.
And yeah, okay. Good. I have one animation. I hope the network is good enough for that. But
We hope
if not,
so.
yeah, if not, then it's not that a big deal.
Anna is here
Hi, Anna.
as well.
The account is online now. Good day, Anna. Can you hear us?
Yes, hello.
Hello. Hi. This is only a test for the microphone and to share the presentation. Okay. I make you presenter. Okay. Could you try to share your presentation?
Yeah, just a moment.
Yes, of course.
See, I'm not very familiar with the WebEx system.
No problem. Okay. It seems very well. Perfect.
Okay.
Could you try to move the slide?
Yes.
Perfect. Okay, it's moving.
Yeah.
Okay.
You can see. Yep.
Perfect. Thank you very much. Okay, so it was well. Okay, now the microphone of Kimmo is very good. I'm sorry, Mr. Rotainen, it's possible if you share your presentation?
Yes, I try. Let's see.
Okay.
Is it now in a presenter mode?
Yes.
Yes,
It's
please.
full screen.
Full screen. Good. And then it changes. Let me check if how do you see this?
Yes, the Earth.
You can see the
Yes, the
animation.
Earth is moving. Yes, perfect.
Good. Great.
Very nice animation.
I'll save the rest. Okay, that's good.
Thank you very much.
Do I need to answer my screen now somehow?
No.
No.
For now, it's sufficient here. It's only a test for the microphone and the video.
Okay.
Ok, perfetto. Francesco, ci mancano solamente Mike e Mariam Salim, che è l'ultimo che è l'ultima persona che presenta.
Fammi vedere se sono nella room 1. Non...
Tra l'altro, per entrare nella room 1, te entri da 2 browser distinti praticamente. Uno con l'applicazione e uno dal browser.
Ok. No, non c'è nessuno nell'altra. Aspettiamo un po'.
Si attende.
Simonetta non c'è.
Simonetta sarà andata a vedere le keynote nella 1 a questo punto. Ma ti chiedevo, ma per accedere anche alla room 1, te entri uno da browser e uno dall'app?
Ma ho fatto uno da browser e uno dall'app. però secondo me è meglio disconnettersi da una perché sennò fa casino.
Infatti non sto andando a controllare se ce la fai te è meglio, almeno insomma lo vedi, ho paura appunto che succeda questo, che me la butti giù.
Ma secondo me loro non si sono, vabbè, comunque penso arrivino, forse arrivano direttamente per l'ora della loro presentazione,
Vabbè, a
poi
quel punto non si fa manco il test, in quel caso.
no. Vabbè, ci sarà la presentazione, probabilmente non hanno potuto
Certo. No, in quella di Mike Swank il problema è che non l'ha messa nemmeno sul cloud.
non ce l'ha,
Non c'è,
questo
quindi se lui non viene com'è no show praticamente,
sì.
in quel caso, perché non ce l'abbiamo sul server. Tra l'altro dal titolo sembra anche interessante. Speriamo ci sia.
Boh, aspettiamo.
Provo intanto a entrare anche io sulla room 1 giù, tanto rientro subito.
And this GS map is now widely used for the
Hi everybody. So just a little notice before starting the works. The keynote in session 1 is finished in this moment, so we have a couple of minutes waiting for the other people that were watching the keynote in session 1 to reconnect, and then the chair of the cryosphere session can start the session on time.
Okay, we can wait a couple of minutes, then we can start. All right, we can start now. Hello, everybody. Good afternoon. I am Francesco Bontomoli from IFAC, and I'm pleased to chair this session. This session, as you know, is about the cryosphere. This is divided in two parts. The next part will be chaired by Simonetta Paloscia, and will begin at 5 o'clock. The session consists of a total of eight presentations, 15 minutes each, included questions. So there are many aspects of the cryosphere covered by this presentation, including many different radiometers with different frequencies, starting from L band, moving up to higher frequencies, so 89 and 243 gigahertz, and also coming back down with the UV radiometer from P to L band. We have 15 minutes for each presentation, and I'll let you know when you have 5 minutes left. So let's start with the first speaker, that is Kimmo Rautiainen from the FMI. And he will present this MOS Level 3 soil freeze and thaw processing and dissemination service. So please, Kimmo, the floor is yours.
Thank you, Francesco.
All right, go ahead.
Okay. Thank you for introducing me. It's very nice to start this session. I'll present the SMOS Level 3 freeze and thaw product developed in Finnish Meteorological Institute in cooperation with Gamma Remote Sensing. This is an operational product. It provides global information on soil state on a daily basis, and the data can be downloaded either from our FMI dissemination services or from ESA dissemination services. The seasonal soil freezing and thawing has many impacts on Earth ecosystems. Global information on soil state is thus an important parameter, and particularly the timing of soil freezing and thawing. It may help various studies related to, for example, climate and climate change. The in situ observations, however, at high latitudes are typically very sparsely located, and also soil state changes cannot be directly linked to air temperatures, since soil freezing and thawing is strongly influenced by different thermally isolating layers such as snow cover and vegetation cover and organic layer. So remote sensing instruments from orbit provide means for direct observations of soil state changes on global scales. And SMOS, being a passive L-band instrument, is particularly good for directly observing the soil. At L-band, there is a strong contrast in permittivity between liquid water and ice. This makes it rather easy to detect the soil state changes with L-band radiometer. Additionally, thanks to low operating frequency, the L-band, the information gathered from the target below is not limited to the very skin of the soil surface. And then we can get information below the surface depending on the soil type and the soil moisture content. Here is image of the SMOS satellite. Very briefly introduced, this mission has been a great success, providing us valuable observations for over 10 years already. And here is shown an animation using SMOS level 3 soil freeze and thaw data. It covers years from the beginning till 2019. The animation is created by Geographics for European Space Agency. I hope the network connection is good enough for this animation to show you. The SMOS freeze and thaw product uses as input data the SMOS level 3 daily gridded brightness temperatures provided by CATDS. The product has 1 day latency. Typically, new daily information is ready at around 4 p.m. UTC time, covering the previous day's soil state situation. Data covers the northern hemisphere and is provided in polar stereographic E-grid projection at 25 × 25 kilometer spatial sampling. The algorithm is based on threshold approach. The soil state in each pixel is given in 3 discrete levels, either frozen, partially frozen, or thaw. Product has been validated using in situ observations and ECMWF reanalysis data. Detailed information on the product is provided in our web page. Data can be downloaded either from our or ESA disseminations servers. In next couple of slides, I illustrate the main steps of our SMOS freeze and thaw algorithm. As I already mentioned, our input data is CATDS daily gridded brightness temperatures. We are using both the horizontal and vertical polarizations, and this data is provided in CATDS database in a global E-grid at cylindrical projection. Here is an example picture of 1 day coverage. In this map, data shown is observed at incidence angle range from 50 to 55 degrees. Currently, we are using this incidence angle range only, but we are developing our algorithm to cover wider range of incidence angles. Originally, this 50 to 55 degrees incidence angles were selected mainly as at those angles, and the effect of the snow cover to the observations was least. Yes, particularly this is true for wave polarization. From horizontal and vertical polarized brightness temperatures, we go to the normalized polarization ratio. That's the next step in the next main step in the algorithm. At the same time, we also change the projection from cylindrical to this polar stereographic that we use also for our output product. And at the same time, we reduce noise by averaging the data. We are using currently 20-day moving average to the data. This map illustrates the polarization ratio for November 1st, 2020, so a couple of days ago. Then we have these so-called thaw and frozen ground references. These are pixel-wise references that are defined empirically using the data observed from the beginning till 2018. These two smaller maps show the two references. Every new observation is always compared to these references. And we actually convert the polarization ratio data to relative values in respect to these references. So in this map, there is the relative normalized polarization ratio shown for the same day. Value 100 equals to frozen soil reference and value 0 to thaw reference. And then finally, the data is categorized to 3 discrete levels. Pixel is defined to be either frozen, that means that about 10 centimeters of soil, depending on the soil type, on average within the pixel is frozen. Or then they may be partially frozen, where part of the pixel is frozen, or then
Kimmo, we cannot hear you. Kimmo, can you hear us? Can you hear me? So it seems that we have problems with Kimmo. Kimmo, can you hear me? So we can wait a little bit for Kimmo. So we can all right. Kimmo, can you hear us?
Kimmo will be back shortly. He didn't notice
Okay.
that his connection was cut.
All right, all right. Since we have, it seems that we have time, since the second presenter is not here, so we also have time to continue and to finish the presentation of Kimmo. Thank you, Hannah. I still continue to see Kimmo on the list of participants.
Now, Kimmo says that he will have to restart his computer because it is completely jammed
All right.
at the moment.
I hope that it will restart soon. Still not appear.
Hello
Right.
again.
Hello, Kimmo.
I had some problems.
Yeah, we noticed.
Actually, I don't know when my connection got broken.
All right, so
I almost finished my presentation here.
But you can, since we have time, a little 10 minutes more, you can resume your presentation and continue it, and then we discuss.
What was the last slide you saw? Can you see my screen now?
Not yet.
Mm-hmm.
If you have problem, Kimmo, we can. Okay, yeah.
So at what point did I lose the connection?
It was after the animation, and
still already this is sound.
Yeah, I think it was more or less at this point.
Okay, I will shortly cover the rest of the presentation. So I was already explaining about the references, the thaw and frozen ground references, how we convert the polarization ratio data to relative polarization ratio. So that at this point the data is scaled between 0 and 100, where 100 equals to frozen soil reference and 0 to thaw soil reference. And finally, we get the categorized soil freeze-thaw data. And the categories are the frozen soil, partially frozen soil, or the thaw soil. And this categorization is based on predefined thresholds for frozen and partially frozen soils. And finally, we remove the obvious errors using ancillary data, the ECMWF 2-meter air temperature and the daily snow cover, so that particularly those cases when we have still summer, but getting false detections of soil freezing, mainly due to the very dry soil conditions, we can easily and automatically remove the false detections. And this is a quick look image that we are providing from our in our dissemination server for quickly checking what is the situation in addition to the actual data. So and here I want at the end show an example of recent validation results. We have compared the SMOS freeze-thaw estimates to in situ data, and in situ data here is downloaded from the International Soil Moisture Network from 5 different networks located in Alaska, US, Northern US, and Canada. The compared parameter here is day of freezing. So the data altogether from 2010 to 2019, and all the data is shown in this scatter plot. So the temporal coverage for different in situ stations varies a lot. Some stations had many years of data, while others had only maybe one year of data. And the X and Y axis in the scatter plot indicate the first day of each year. We have data from in situ station after which the soil has been frozen for 10 consecutive days, for both defined from both in situ and from SMOS data. And for the in situ, we used both soil moisture and soil temperature when we were defining whether the soil is frozen or not at the sensor location. So the results here show a good correlation, 0.75, the correlation actually, and the overall bias is practically zero. However, the root mean square error is about 15 days. So, but considering that the SMOS and the in situ data has totally different scales, from tens of kilometers for SMOS and a point measurement for in situ, these results to me are very good. And the final summary. So we have developed an operational freeze and thaw product based on SMOS observations. The data are available from FMI and ESA dissemination services. We hope that the science community finds this product, and we encourage people to use and test it, and then we highly appreciate all feedback from people who are testing this data. Internally at FMI, we have also used the product in another ESA study calling Solving Methane Fluxes at Northern Latitudes using atmospheric and soil earth observations data. And in ESA web pages, you can find more information of this project. But one important observation during that project has been that, or that study has been that constraining the winter methane emissions with SMOS soil freeze-thaw data improved the inversion model performance. Okay, that's all. Thank you for your attention.
Thank you, Kimmo. Thank you for this nice presentation.
Sorry for the bad connection at some point.
Yeah, it's something happened with this kind of events. And okay, so we have time for questions from the audience and also from the YouTube chat. Is there any question? Okay, Kimmo, I have a curiosity about the partially frozen classification. So, what do you mean? Can you comment a little bit more on this?
Well, the SMOS pixel is rather large, so it's typically not all the soil within the pixel freezes at the same time. So it's common that the signature of the observation starts to go from a thaw state to frozen state gradually, and before it saturates, we are somewhere in between the thaw and frozen state. So we assume that while the signature indicates something in between the frozen and thaw states, then there may be that partially the soil pixel is frozen, or then maybe that very, very thin layer of soil is frozen. That's just to indicate that there is a kind of a transition phase in between thaw and frozen states.
All right, thank you. Is there any further questions? No question. So, Kimmo, another point. You showed the validation with in situ measurements. Is there? Yeah, that one. Where these stations are located? I mean, is in the whole Finland?
No. These are mainly in Alaska and northern US and Canada. I think mostly from Alaska. So these are the SNOTEL and SCAN networks from US and yeah, Northern America.
Yeah. It seems a pretty good agreement.
Yes, of course, we have been screening some of the stations based on whether there is open water nearby or within the pixel that the SMOS measures, or if we have tried to analyze whether a station represents well enough the whole SMOS pixel.
Okay. All right. Thank you, Kimmo.
Thank you.
All right. I think it's time to move to if there is not any other question, to the next speaker. I will introduce next speaker, which is Anna Kontu from the Finnish Meteorological Institute. And Anna will talk about the boreal forest L-band observation. So please, Anna, the floor is yours.
Okay, can you now see my presentation?
Yes.
Great. In my presentation, I'm looking at boreal forests at L-band, and with the main idea is to try to remove the effect of forests from satellite measurements. So the motivation for this work is that when doing MicroRad remote sensing of snow and soil frost in areas covered with seasonal snow, most of them are covered also with forests. So we need to model those forests in order to remove them from the signal. And often, for example, in the SMOS algorithms, the canopy transmissivity or the vegetation optical depth is modeled as a function of biomass only. But in our measurements, we have seen that the transmissivity also varies with temperature. And also, so many of these models which are used in forest to model forests, they are based on like short campaign measurements. So there is no real changes in temperature in the model data. So the goal of this work is to define a model for the temperature dependence of boreal forest transmissivity at L-band, especially in freezing conditions. So I'm not looking at temperature changes above 0 degrees. The background why the transmissivity has or changes with temperature is, of course, because the relative permittivity of liquid water is different from the permittivity of ice. So if we're looking at soil, there almost all of the liquid water freezes when temperature drops below 0. But the trees have natural mechanisms to cope with the freezing conditions, and therefore water can stay in liquid state even down to -40 degrees. And because of these processes in the trees, the permittivity changes gradually when temperature drops below 0. So there is no fast freezing point when temperature drops below 0. So in Sodankylä in northern Finland, we have this kind of measurement setup with a 24-meter tower where we have 2 ESA L-Bara instruments. One of them is located on the tower at 21 meters, so it is above the forest canopy, and the other one is on the ground, so it looks at the canopy from below. Measurements began in late 2018, but we have good data since January 2019, and measurements are still continuing at the moment. The area, it's a sparse pine-dominated forest and sandy soil, so it's kind of typical boreal forest. And in addition to these radiometer measurements, we have lots of reference instruments, some embedded in the tree trunks to measure their permittivity and skin temperature, and then also stations to monitor soil, snow, and meteorological parameters. This is a drone image of the measurement area. So you can see the two L-bars in the center and their measurement area on the ground. And then the tree trunk sensors are right next to the tower, but the other stations are a bit further away, but very close to the tower anyway, so that their data is represented. To derive the forest parameters from this MicroRad data, I'm using this two-stream electromagnetic model developed by Mike Schwank and his team. So in these typical applications, these kind of simple tau omega models are used, and they only model vegetation by taking a reflection of the vegetation signal from the ground. But in this two-stream model, there are reflections and scattering in the atmosphere. So it's more a complicated model, which is better suited for this kind of dense scattering vegetation, like a forest. The retrieval or here you can see the sketch of the measurement. So we do hourly elevation scans with both of the L-bars. So we can actually measure the canopy from both directions in different elevation angles. And we can measure this background sky radiation as well as background soil radiation also. So the retrieval approach is that first we retrieve the vegetation optical depth from this measurement below the canopy and from sky measurement. Then we could also soil permittivity from this ground measurement, but because we have also soil permittivity measurements, I have used the data and not the retrieved signal there. And then the single scattering albedo omega of the canopy can be retrieved from this measurement from above. But the results that I show here are only from the first step. This is still like an ongoing work, so that's where I'm at the moment. This figure shows the tree relative permittivity in the top panel and the tree skin temperature in the bottom panel. So you can actually see that in the winter, so that is here in the beginning and here at the end, the relative permittivity follows very closely the temperature of the tree skin temperature. But here in the summertime, there the relative permittivity is very stable, even though temperature changes. So there is no relationship between permittivity and temperature in the summertime. But I'm focusing here on the wintertime measurements. And this figure shows data from 2019. This is the retrieved canopy transmissivity in one elevation angle as a function of tree skin temperature. So you can see that there are like 3 different phases. When temperature is above 0, there is very little change in the transmissivity signal. But then when trees start to freeze, there is first a very rapid change where transmissivity increases quite a lot. And then when temperature gets colder, there is this gradual increase in transmissivity, so that when you get to very cold temperatures like below -30, the canopy is actually transparent. Transmissivity reaches 1. And you can see the same in the vegetation optical depth also. So very low or very little change above 0, then the rapid change right below 0 degrees, and then the gradual change when it gets colder. So this, when you plot these parameters against temperature, these graphs are very clear. But then if you look at the time series, there's lots of changes because air temperature changes all the time. So actually the transmissivity of the forest changes very rapidly during winter. Then this figure shows just all the measurements from 2019 plotted as the function of elevation. So this change in one elevation angle comes from, or this is all the measurements that we have from that elevation angle during the year. So there's lots of variation as from the temperature changes, but also from other sources possibly. And still at the moment, because the forest biomass changes between these different elevation angles, we cannot use multi-angle measurements, or we cannot determine this transmissivity as a function of elevation. But this is a kind of work in progress, so that we actually now have a data set of 3 measurements from that area. You can see this is our measurement tower here, and one of my colleagues measured the coordinates and height and width of each tree in this measurement area, so that we can now calculate the biomass that is in each measurement footprint from this data. So this will result in a model of tree transmissivity, both as a function of temperature and the biomass. So as a conclusion, we can see variation in transmissivity from 0.5 to 1 during the winter, and rapid changes when the temperature changes. And this work will continue, so that in near future, we will have this model for transmissivity as a function of temperature and biomass. Okay, thank you.
Thank you, Anna, for this very interesting work. If I ask the audience if there is any comment or question to Anna. It seems that we don't have questions. So I have a curiosity about this. You said you showed the dielectric constant. Did you develop a model of the electric constant for temperature? I mean, below 0 of the trees, or did you fit in some way the model with your measurement? How do you do that?
Actually, I haven't used the real permittivity measurements here. The electromagnetic model doesn't need the permittivity of trees as such. So I just used the temperature measurements to plot this, to show the retrieval results just as a function of temperature. So that those 3 measurements are actually not used in the retrieval process itself. So I don't have a model for the tree permittivity as a function of temperature, at least at the moment.
All right. So, and what would you, I don't know, what would you will you develop some other experiment in the future for better assessing this idea, this concept?
Sorry, could you repeat that?
What do you think about the future experiment to better assess this transmissivity that you have found? You have some plan to go on with this experiment?
Yes, at the moment we are continuing the experiment probably as long as ESA will loan these radiometers to us, because right now we only have them always for the next year. Yeah, we will. I think we have some plans of increasing instrumentation at the area, and of course we are only now really getting to look at the data. So lots of data analysis and processing still to do, so that we can get down to the like explaining why everything we see there, or what is the real cause for these phenomena. Let's see.
All right. Thank you, Anna. Thank you again. And I will introduce the next speaker, that is Kirsty Weifel. Kirsty will present us the validating a snow surface radial transfer model between 89 and 240 gigahertz using airborne observation over Arctic tundra. So Kirsty, welcome, and the floor is yours.
Thank you very much. I'll just share my screen. Let me know if you can see this.
Yes.
Great.
Very good.
Yeah, so I'm going to be presenting some work, which is a collaboration between the Metafis and Northumbria University in the UK, validating snow surface radiative transfer model from 89 to 243 gigahertz using urban observations. And this is work with colleagues mentioned here, Mel Sandals, Nick Rutter, and Stuart Fox. So just to give a quick overview, I'll run through why we're doing this work, the data and our methods based on the observations collected during a field campaign. I'll then give just an overview of some of our initial results validating brightness temperatures from the snow microwave radiative transfer model, SMRT, and then go on to quickly mention our plans for future work, and then I'll sum up. So motivation. Satellite microwave radiance observations in polar regions have a positive impact on NWP forecasts, both in the Arctic and at mid-latitudes, but they are often rejected as it's difficult to account for the surface contribution. Being able to accurately model snow surface emissivities would allow the surface affected radiances to be assimilated, but because snow emissivities are highly variable and depend on the snow microstructure, it can be quite difficult to model. So we're working on validating the snow microwave radiative transfer model, as I said, at key atmospheric window and sounding frequencies from 89 to 243 gigahertz, to explore the potential for modeling surface emissivity, which could have particular benefits for assimilation of the 183 gigahertz water vapor band. So to do this, we're using data from the Maximize field campaign, which took place at Trail Valley Creek in March 2018 and involved groups from the Metafis, Northumbria University, Edinburgh University, and the University of Sherbrooke in Canada. During the campaign, airborne microwave radiance observations were collected using the FAM aircraft with a number of flights flown over Trail Valley Creek. And these observations were co-located with ground-based radiometer observations at 89 gigahertz only, and also in situ vertical profile measurements of snow properties, including depth, temperature, density, and specific surface area for 29 snow pits. The locations of the snow pits were chosen to try and cover a range of topographies and aspects to represent the wider Arctic tundra that we were targeting. So the in situ snow pit measurements were used as input to SMRT for passive simulations of microwave brightness temperatures for 3-layer snowpacks. So the figure at the bottom there just shows the stratigraphy of our 29 snow pits and shows the 3 main layers where SS is surface snow, WS is wind slab, and DH is depth hoar. And these are typical layers in Arctic tundra snowpacks. The benefits of using a 3-layer snow model as opposed to a single-layer model is that the frequencies we're interested in, penetration depths are relatively shallow. So you get different sensitivity to the different layers depending on what frequency you're looking at. For example, higher frequencies are more sensitive nearer the surface in lower density, higher specific surface area snow layers, while the lower frequencies will penetrate deeper into the snowpack and potentially be viewing the substrate beneath the snow as well. Another key feature of our analysis was the inclusion of an anisotropic atmosphere in SMRT simulations. So this used the Atmospheric Radiative Transfer Simulator, ARTS, to simulate atmospheric downwelling for the full atmospheric profile, as well as absorption and emission for the layer of atmosphere between the surface and the aircraft, for better comparison between our airborne observations and our simulations that were surface-based. So the figure on the right here just shows how our flight tracks coincided with the locations of the snow pits, which are shown by the blue crosses. And the different grid squares here just show different areas of interest that we were targeting. This also highlights the 3 broad topographic classifications that we were thinking about. So plateau, valley, and slopes, which again are typical of the wider Arctic tundra area. So going on to look at some of our results, it's first worth noting that this analysis all focuses on nadir-looking brightness temperatures. So we're not really considering the impacts of polarization at this point. So we started by comparing our SMRT simulated brightness temperatures with the ground-based radiometer observations at 89 gigahertz, which you can see in the figure here. The range in the SMRT simulations, which are given by the error bars, represent the variability in our observed snow properties, specifically the ranges in observed density and specific surface area for each of the pits. So you can see from this that SMRT showed reasonable agreement with the ground-based observations in most cases, except for 2 pits that saw no crossover with the observed brightness temperatures, which were the pits shown here, AO6S1 and AO3C1. But we were able to attribute this to a low surface density in the case of AO3C1 and a low wind slab specific surface area in the case of AO6S1. And we were able to improve these simulations when we replaced those values with median values for Trail Valley Creek. So this figure now compares the SMRT simulations for all 29 snow pits, again shown by the blue error bars, with the airborne observations. And here you're seeing, so the airborne observations are the box and whiskers, and here you're seeing observations for a particular topographic classification that coincides with the classification of the pit. So wherever the pit was dug, if it was dug on plateau, then you're seeing all the plateau observations within that area of interest. And the ground-based observations are shown by the red error bars, but you can see that they weren't available at all of our pit locations. But where they were available, we've included them here. So of our 29 snow pits, only 4 had no overlap between the range in SMRT simulated brightness temperatures and the range of observations, which included the 2 pits that also underestimated the ground-based radiometer observations that we saw on the previous slide. So that's these 2 here, if you can see my mouse or not. The other 2 pits that are highlighted here, which had the warmest simulated brightness temperatures, were interesting because the simulations were in good agreement with the ground-based observations, but not with the airborne observations. These pits were actually found to be the deepest and were dug in snow drifts. So we believe that these kind of smaller scale surface features weren't captured by the airborne instrument footprint for the flight track on that day. Hence the reasonable agreement with the ground-based observations, but not with the airborne. But from this it seems evident that the range in SMRT simulated brightness temperatures that we get when we account for variability in our observed snow properties can represent airborne observations, 8 to 9 gigahertz, for a lot of our pits. So moving on to think about our simulations at higher frequencies now. The importance of the atmosphere becomes more apparent. So this figure here just shows histograms of airborne observations in orange at 89, 118, which is a temperature sounding channel, 157, 183, which is a humidity sounding channel, and 243 gigahertz. And these are compared with SMRT simulated brightness temperatures with and without the inclusion of the simulated atmosphere in pink and blue. So blue being without a simulated atmosphere and pink being with the atmosphere. And what this shows is that at the higher frequencies and at the sounding channels, which were 118 and 183, without the inclusion of the atmosphere, SMRT quite strongly underestimates observed brightness temperatures. So here again, you're seeing airborne observed brightness temperatures shown by the box and whisker plots, and SMRT simulated brightness temperatures shown by the blue error bars, this time grouped according to the broad topographic types for Trail Valley Creek that I mentioned before: plateau, slope, and valley. And while these results suggest there is overlap between our simulated brightness temperatures and observations at all of our frequencies, there is greater uncertainty in our simulations at higher frequencies. A lot of this is due to limitations of the improved Born approximation, which is the electromagnetic model used within SMRT. And at the same time, this is data from one of our flights, and we have other flight data where the agreement was good at 89 gigahertz, but not at the higher frequencies. And we had lower observed brightness temperatures that weren't replicated in our simulations. So we expected some pattern in the simulations for pits that were dug on the same day as a flight, for example, but this didn't seem to be the case, so work is still ongoing to understand why that might be and how we can improve our simulations at higher frequencies. Going forward, we're continuing to work on validating SMRT, in particular, as I said, looking at where simulations didn't agree with our observations and why. And we're also looking at simulations of emissivity as well as brightness temperature. And long term, in the future, if the validation proves successful, we'd hope to be able to couple SMRT to a land surface model, such as JULES, which is a Met Office land surface model, which would provide information on the snow microstructure. And also to be able to couple SMRT to RTTOV, which is the radiative transfer model used in operational satellite data assimilation.
Thank you, Kirsty,
So,
for this. Sorry.
Sorry, just
Sorry,
to sum up now. So I said the aim is ultimately to improve the assimilation of surface-sensitive satellite radiances in NWP systems. A first key step of that is to improve our modeling of surface emissivity, for which we're assessing the use of SMRT. We've shown that SMRT can produce realistic simulations of ground and airborne observed brightness temperatures at 89 gigahertz, but there is greater uncertainty at higher frequencies. And as I said, work is ongoing to understand why. We don't always have agreement. But I've also highlighted the importance of accounting for the atmosphere in simulations, particularly at higher frequencies and atmospheric sounding channels. And finally, I would just like to mention the individuals and organizations named here who were involved in the collection of field data and some references. So thank you very much for listening.
Thank you again, Kirsty, to show us this nice presentation and this nice work. Do you have from the audience some questions? And also from the chat of YouTube? Seems that there is no question. So, Kirsty, which is, I'm curious about the effect of the soil on this measurement, for example, at the lowest frequency that you have, I guess that the soil effect is quite weak, but yeah, can you comment a little bit more?
So within our simulations, we're using just a quite a simple flat soil substrate with a constant temperature. So we're not doing too much to simulate any changes in that to see what effect that might have. Obviously, we're considering what effect we get from the soil when we're thinking about, as you say, the lower frequencies where we might see some effect. So this has proved obviously be quite dependent on the depth of the snow pits. So we've kind of run some sensitivities varying snow pit depth to see kind of how much change we get when we think it's deep enough that we're in fact sort of it is something that we're considering, but at the moment we've not simulated anything to compare different types of substrate. For example, there were other pits that I haven't mentioned here that were dug over lake ice. So in the future, we'd hope to try and understand more about how our simulations might be affected by whether you're looking at snowpacks on land, so over soil substrates or over ice, for example.
Thank you, Kirsti, again. So let's move on to the next speaker, that is Christopher Bert. And Christophe will talk about the estimating Arctic sea ice distribution for SMOS, multi-incident angle, brightness temperature under unsupervised learning algorithm. So please, Christophe, the floor is yours. Can you show the presentation? Okay, yeah.
Can you see my screen?
Yes.
Okay. So good afternoon, everybody. My name is Christoph Herbert, and I'm working at the Polytechnic University of Catalunya in Barcelona. And I would like to present our current work on the segmentation of Arctic sea ice from SMOS data using unsupervised learning algorithms. SMOS brightness temperature observations at L-band, around 1.4 gigahertz, are known to be sensitive to a sea ice thickness up to around 60 centimeters, and therefore the currently provided maps of distribution of thin sea ice in the Arctic are based on that SMOS data. But apart from the sea ice thickness, however, the signature of SMOS observations do also depend on various sea ice parameters such as surface temperature, layering, heterogeneity, and snow cover. And this is why additional information has to be added and several assumptions have to be made to retrieve any ice physical parameter. For as an example, for sea ice concentration, it's often underestimated in regions of particularly thin ice and vice versa. And also a strong regional and seasonal variability of the physical composition of sea ice and also the limited availability of validation data makes sometimes an accurate estimation of sea ice thickness challenging. So our objective here, so since satellite observations of SMOS are itself very accurate, our aim is here to harness the information about the composition of sea ice, which is contained in brightness temperature observations at multiple incidence angles. And the approach is to combine the observations in an unsupervised manner to segment Arctic sea ice into a number of classes. And here we consider the spatial and the statistical characteristics of the observations. And our main interest here is to find the relationship between the observations by using their similarities and differences for specific ice types or sea ice properties, including surface types and thickness ranges. And we want to study the performance matrix to analyze obtained classes in terms of their separability, temporal stability, and model uncertainty. So prior to segmentation, we have to define input features from the observations, and they are selected in order to make use of the full information of the SMOS data and to increase the sensitivity to the actual sea ice properties. So we made two pre-steps. The first step is that brightness temperature is corrected using existing maps of sea ice concentration from OSISAF to obtain the brightness temperatures of the actual remaining sea ice. And we dropped low concentrated areas with a concentration below 50%. And in the second step, we combined the vertical and horizontal polarizations to reduce the direct effect of the physical surface temperature by computing the polarization ratio and only be left with the emissivities. And the polarization ratio has the advantage that it still maintains a sufficient dynamic range to discriminate sea ice types and thickness. And also what we found out is the information content is higher, like using only SMOS is higher at larger incident angles. So you can see here what we chose, like the four high, like a total of four incident of polarization maps of 3 incidence angle with high values between 40 and 56 degrees. So the algorithm here has as an input the 3 polarization ratio maps, and the proposed unsupervised machine learning approach is based on a Bayesian inference framework where we indicate spatial patterns of sea ice according to a number of most relevant brightness temperature observations. And the segmentation is based on a hidden Markov random field, which is used to consider the spatial dependencies of the observations and the statistical characteristics using a Gaussian mixture model. And then after segmentation, it results in clusters, and these clusters are described by a set of multivariate Gaussian distributions and the spatial patterns of pixels in a so-called latent field. And model parameters consist of the means and the covariances of the clusters in the so-called feature space and the latent field in physical space. So the Arctic region is then segmented independently for 5 days intervals during the periods of late summer melt and early freeze up from September to December 2016. And the number of classes is chosen beforehand according to the distribution of the PR values and justified a posteriori from the separability of classes. And the model uncertainty is quantified from the obtained class membership probabilities using information entropy. And here we can point out either uncertain regions between or in a certain class and boundaries of higher uncertainty between two classes. So in the first step, the spatial patterns were compared to a current SMOS sea ice thickness product provided by the Alfred Wegener Institute of Polar and Marine Science in research in Bremerhaven. And we classified the labels according to the temporal evolutions of the polarization ratio values and the range of sea ice thickness values found in the current SMOS sea ice thickness product. So in total, we found 3 significant or principal classes. They're namely thick sea ice with low polarization values, where the thickness is close to sensor saturation. A class which is denoted by a transition zone, where we have a large variation of sea ice thickness. And thirdly, newly formed thin sea ice, which appears from the beginning of the freeze-up period. So the idea is now to evaluate the performance of the segmentation by analyzing the classes statistically in marginal feature space. So although you can see here that the correlation is quite high between the features, the characteristics of the statistical model parameters are different between the clusters, and we can use the mean and the covariances to analyze the shape and the location of the clusters. And the classes itself can be evaluated in terms of their correlation and separability. And so if you have a look at the temporal evolution of the obtained class mean values and the standard deviations, which are again obtained from the covariance matrix, can be investigated along the study period. And if you have a look, you can distinguish two subperiods. The first one is the late summer melt in the beginning of September until we have the sea ice minimum, which is where we can only find two separable classes. And when the temperatures drop long enough below the freezing point of seawater, thin sea ice starts to form, and an additional significant class is recognized. So, and then we can see that the thick sea ice class is very stable along the entire study period. And here we can see that the new class appears in the beginning of the freeze-up period, and as the period continues, it becomes less separable, and we can see an overlap with the transition zone cluster. So in order to quantify these overlaps between the clusters, classes are analyzed in terms of their intercluster separability. And here we are using a geometric separability index, which is based on nearest neighbor comparison to indicate how much clusters actually overlap. And so a value of 1 means perfectly separable, and the value of 0 means completely entangled. And we can see that we have a very good separability using two classes in the beginning, in late summer melt, and 3 classes from the beginning of the freeze-up period. And we can also see that the thick sea ice class is always highly separable along the entire study period, and the separability for thin sea ice is very stable in the beginning, or very separable in the beginning, and it starts to vary. What we found out that it comes from it results because the relative amount of new sea ice decreases as the sea ice extends, and the significance of these particular classes is going to decrease. So what we did is we proposed a novel data-driven approach to segment the Arctic sea ice into a number of classes. And these classes could be mainly attributed to thickness ranges so far. And we analyzed the classes in terms of their separability and temporal stability along the study period. And we with which we quantified the performance of our segmentation approach. And so we reduced it to a number of significant classes, so which these classes are stable and separable, and we could find their physical meaning. We can try to infer this class or classify this class more precisely. And so far, if you want to have a look, we actually submitted our research to Geophysical Research Letters, and you can find the manuscript in the archive already uploaded. So future work is 3 different things I want to mention. So first of all, that the class mean values which are formed by a segmentation are the most significant values, and they could be used as dynamic tie points. So which we characterize when we manage to characterize that dynamic tie points and their variation. These are the most significant values in the class. And The method can be also applied to any multi-source spatial data set, so to combine different sources, such as, for example, if you have given images in missions where we have multiple frequencies available, they can be combined if you have any spatial data set available. And the aim would be always to understand the link between the observations in a specific class, which means which is referred to a specific physical property. And the algorithm can also be combined with the physics-based method, such as, for example, the radiative transfer model, to increase the retrieval performance of common sea ice products. So thank you very much for your attention, and yeah, I'm happy to answer your questions now.
So thank you, Christophe, for this such a great presentation. I ask the audience if there are any questions for him. Also from the chat of the YouTube. No question.
And maybe.
Okay. Yeah, Lars.
One.
Yeah.
So what
Yes,
would
please.
be the advantage of having classes that are aligned to the thickness, which can be detected with other methods? So is there any new knowledge that you generate from this?
Yeah, yes, Lars, thank you very much for the question. So the method has several advantages. So first of all, that we consider the spatial correlations in the methods, because we are using not only the statistical model parameters, but also a directional heterogeneity coefficient, so that we cluster this the classes by basically defining that neighboring classes are likely to have the same class, to belong to the same class, and in an updating process, the statistical parameters, let's say the means and the covariances, are updated alternatively with the spatial correlations, and the advantages would be that so we try to include always multi-dimensional data sets. So if for example, if we have a snapshot of a specific area, and we have different data sets, we can find the correlations between the data. And so what we did is we used the multi-incident angle data set, and because we try to find the information in between these data sets, because it's like in most of the products, it's kind of neglected, and only lower incident angle values are used and averaged. And we try to make the full use of so to make a data-driven approach and making the full use of the brightness temperature. And then, of course, like as you say, these classes, when they're quite stable, then another model can be applied, or physics-based model could be applied to the single classes. But these are basically the most significant classes which could be formed only based on the brightness temperature observations.
Okay, thank you.
Okay, thank you very much for the question.
All right, thank you again, Christophe. It's time to move to the next presentation. That is from Mustafa Askoi, that he will present the passive MicroRad response to the Antarctic and Greenland ice sheets. So I give Mustafa, I leave the floor to you. Maybe you have to unmute yourself. Oh,
Thanks,
yeah.
Francesco. Thank you. Good morning, good afternoon, or good evening, everyone, wherever you are following this conference. My talk is about passive MicroRad response of the Antarctic and Greenland ice sheets. And first of all, I would like to acknowledge my students, my undergrad and graduate students who did most of the work Angel Pertiga and John Bradburn here at University at Albany. The motivation of our study is, previous studies have demonstrated certain properties of Antarctic and Greenland ice sheets, such as grain size, density, surface and subsurface temperatures, can be estimated using microwave radiometers operating in L, K, and Ka bands. However, the complete microwave response of these two main ice bodies across the entire microwave spectrum from L to W band is mostly missing in the literature. So we try to utilize simple microwave radiation and ice sheet physics models to analyze the sensitivity of surface brightness temperatures of these ice sheets to their specific thermal and physical properties across the microwave spectrum up to 100 gigahertz. And the goal is to provide an insight for future designs of remote sensing missions that will target these ice sheets by demonstrating the optimum frequencies of operation to retrieve desired ice characteristics. And our study assumed these ice sheets as planar layered media, as you can see from this picture. And each layer of ice has its temperature, density, and grain size, and we assume they are fixed and constant in the entire layer, but of course different from one layer to another layer. And we assume 1 centimeter layers, and it was based on the in situ measurements done in Antarctic ice sheets. The layer thickness values we took, they changed from 1 centimeter to 3 centimeters, so we assumed a 3 centimeter layer. And regarding the physical temperatures of ice, we basically took the measurements done at Dome C in Antarctic ice sheet down to 21 meter as reference, and they of course depend on the season. They are changing basically from 1 month to another month, so we take it as a reference. And in deeper ice, we basically assume that the temperature is increasing linearly with the defined by a variable Q, which basically the gradient of the temperature increase versus that. For density, we assume an exponentially increasing density profile where we have a densification parameter H, and plus, of course, the density is assumed to be a noisy variable. And we have the standard deviation of that noise and the decay in that noise versus depth. So we basically have 3 variables in our model regarding the density of ice. And for grain size, we basically assume an increasing grain size with depth. And the variable, again, in our model was the gradient regarding grain size, which defines how grain size is increasing versus depth. So we basically assume a planar layered media and assume some simple models for the physical temperature of the ice, density, and grain size. But we basically leave some variables in our model so we can play with them to see the sensitivity of surface brightness temperatures to each of these variables. And again, we assume a simple radiation model to calculate the surface brightness temperatures. So this is the surface brightness temperature. Is basically this is the thermal radiation, and it's basically from the thermal radiation from each layer is being attenuated up to the surface. And of course, we included the impacts of the reflections between layers as well. And we basically can write this model as even a simpler model using a weighting function here, and basically the integral of weighting function multiplied by the physical temperature of ice will give us the surface brightness temperature. And basically to analyze which frequencies are sensitive to which depths across this microwave spectrum, we defined a normalized weighting function. And using that normalized weighting function, we define two variables. The first one is the average. It's called the average depth of sensitivity. It's basically the depth where the layers above and below of that depth is contributing equally to the surface brightness temperature. And the other one is the penetration depth. It's basically the depth where the maximum where the weighting function decays to its 1 over E. So it's a very typical definition of penetration depth. So we basically use these two different depth parameters to see which frequencies are sensitive to which depths in the ice sheets. And to validate, we wanted to validate these models, and we tried to simulate brightness temperatures over Concordia station. And again, we use these measured in situ subsurface temperatures down to 21 meter, and these are measured by a group led by Dr. Brooker between 2006 and 2010. And you can see how they are changing in different months. And we again used a simple density and grain size models based on profiles based on the models that I just described. And we try to calculate the surface brightness temperature using our radiation model. And we try to compare the simulated brightness temperatures with measurements done by GPM constellation members, specifically SSMIS and AMSR2. We took these two satellites because they are polar orbiting satellites within the GPM constellation. And GPM constellation is providing intercalibrated brightness temperature measurements. So basically, we can combine different channels from these two instruments. We can combine them and use them as a single instrument from C band to W band. The minimum frequency channel is 6.9 gigahertz, and the highest frequency channel is 91.6 gigahertz. So we can cover the entire microwave spectrum from from C to W band. We didn't include L band in these studies because it requires an intercalibration as well. So for this analysis, we just focused on the intercalibrated GPM constellation measurements. Although 6.9 and 7.3 gigahertz measurements are yet to be intercalibrated with the rest of the channels, but since they are coming from the same instruments, we basically took them in our analysis and we included them. So these measurements were used to validate the ice sheet physics and microwave radiation models I just introduced. And here you can see the average
Sorry,
depth
if I interrupt you, you have 5 minutes. 5 minutes left.
Okay, all right. So here you can see the average depth of sensitivities for different GPM channel frequencies. So you can see the average depth of sensitivity decreases from 40 meters at 6.9 gigahertz to basically just limited to the surface at 90 gigahertz. Here is the plot. And we basically compare the internal physical temperatures of ice sheets at these depths with the surface brightness temperatures measured by the GPM constellation, and look at the correlation between them. And here you can see from 6.9 gigahertz to 90 gigahertz. So we see that these surface brightness temperatures and the physical temperatures of ice sheets at average depth of sensitivities, they are very highly correlated, which is promising for our modeling and radiation studies. And also we look at the penetration depths, and they are a little bit higher than the average depth of sensitivity. We basically calculated the penetration depths, and they are basically changing from 2 kilometers to a few tenths of centimeters, from 1 gigahertz to 100 gigahertz. So operating wideband radiometers or multi-frequency systems may enable profiling ice properties versus depth from surface to very deep ice. And to look at the frequencies, specific frequencies where the surface brightness temperature is very sensitive to specific ice properties, we try to change the model parameters. We try to vary them and look at the brightness temperatures. So basically, we change how the internal temperature is increasing in deep ice. We change the densification value. We change the standard deviation of the noise in the density of ice, and we basically change how that noise is decaying and how grain size is increasing versus depth. And then we calculated the surface brightness temperatures and calculated the sensitivity, where the sensitivity is defined by the brightness temperature change divided by the change in that specific parameter. And here you can see we basically look at the month of the year, internal flux, which is how the temperature is increasing versus depth, densification, the standard deviation of density fluctuations, damping in these density fluctuations, and grain size gradient. So here you can see the month, basically the high frequencies V and W bands are most sensitive to the internal the surface temperatures and internal flux and damping in density fluctuations and the density fluctuations themselves. Basically, lower frequencies are very sensitive to those parameters. And if you look at the densification, it's basically Ka and V band. They are the frequencies sensitive to these properties. So it's basically in future radiometer designs, I think we should consider these kind of analysis to pick the best frequencies to retrieve certain ice properties. And to this conclusion, so we conclude that brightness temperatures of ice sheets in Antarctica and Greenland, they are sensitive to various physical and thermal properties, and future remote sensing missions targeting these properties should be designed accordingly. And wideband radiometers can be designed, multi-frequency systems can be designed, and also like constellations like GPM can be used for retrieval of such properties, because GPM has basically frequency channels where these the surface brightness temperatures are sensitive to these properties. So it's a very good opportunity. And right now, our main challenge is matching our brightness temperature simulations with radiometer measurements across the wide spectrum from L to W band. I showed the correlations, but matching the exact brightness temperature values are challenging. When we kind of tune our models to lower frequencies, we are getting larger errors at higher frequencies, or vice versa. So in the literature, they are basically tuning the models by putting some factors in grain size, etc. So we are basically trying to come up with such a solution to cover the entire spectrum up to 100 gigahertz. So that's a quick summary. Thank you very much. And if you have any questions, I'm happy to answer them. So thanks.
Okay. Thank you, Mustafa, for this interesting presentation. If we have one quick question for him.
Yes, I have a question. Did you take any scattering into account within the ice?
Yeah, I mean, right. We are considering Rayleigh scattering, and that's maybe one of the reasons that we are having large errors at high frequencies. So we may need to switch to other scattering mechanisms, like maybe Mie scattering for high frequencies, because the wavelength is comparable to grain size at those frequencies. So right now we are using Rayleigh scattering.
Yes, and you could have multiple scattering as well. I mean, as the frequency goes up.
Right. Yeah, that's something we can consider as well. Yeah.
How do you think this would affect your higher frequency results?
Mm-hmm.
Yes.
So yeah, that's the thing that we are.
Thank you. So you can discuss privately. It's time for another presentation. The next presenter is Marco Brugioni from IFAC, and we present the result of the first ultra-wideband microwave radiometry campaign in Antarctica. So Marco, I leave the floor to you.
Okay, so we are going to the lower end of the microwave spectrum this time. We are going even lower than L-band. So I'm going to present the first result of the first ultra-wideband microwave radiometry campaign that we performed in Antarctica in 2018. Sorry. Okay, so basically, I want to stress a little bit the justification why we have to go at lower frequency. I mean, lower, when I say lower, I mean P-band, 500 megahertz and slightly above. The basic point is this one. Up to now, microwave radiometry has been performed in protected bands. And the protected bands are really narrow bands going from 1.4 gigahertz up to 90. The basic point is that we miss a lot of part of the spectrum, which usually cannot be measured because of the artificial emission, which is allocated for broadcasting. I mean, mobile phones and so on. However, going deeper could be really benefit for study the cold regions, and this has been demonstrated in the last years, especially at L-band, when we have been able to develop new products for the sea ice thickness, where we have been able to estimate the internal temperature of the ice sheet in the part of the ice sheet where the ice is in steady state condition. But however, the key point is that if we can go deeper and we can penetrate deeper inside of the ice, we can try to retrieve a lot of parameters which at the moment are forbidden. And I mean, sea ice thickness for really thick ice, also sea salinity at high latitude, deriving the permafrost temperature status, active layer thickness, and also the temperature of the first emitter, or also derive the internal ice sheet temperature much more deeper than what can be at L-band. This because the ice permittivity is characterized by a very low imaginary part and permits to the wavelength at P-band, P12 band to penetrate very, very deep inside of the ice. This is the main reason why the ultra-wideband microwave radiometer has been developed, mimicking the atmospheric sounder. You have already seen, for those who have attended the presentation of yesterday and the day before yesterday by Joel Johnson, so you can have an idea of how the ultra-wideband microwave radiometer works. The basic point is that continuously sampling the microwave spectrum allows for a fine spectral resolution and also an efficient mitigation of RFI. You have to think that in this spectrum, in this part of the spectrum from 500 megahertz to L-band, 1.4 gigahertz, you have the broadcasting of the television, which is not present over the ocean and over the ice sheets. We have the mobile phones, which are not present there. So this part of the spectrum can actually really exploit it for these regions. The ultra wideband, I'm going pretty fast on this, has been developed in a NASA instrument incubator program, started in 2013, and the project was led by Ohio State University and was aimed at develop this spectrometer which worked from 500 to 2000 megahertz. I mean, 2 octaves, and was deployed on board of the Twin Otter, which is this plane here, in 2018 in Antarctica and into previous campaign in Greenland. So I'm going straight. So the basic point is this one. Here you have a very sketch, very schematic of the scenario that can be benefit for, I mean, the polar scenarios that can benefit from this kind of measurements. And we go from the sea surface salinity in cold water to the estimation of sea ice volume, the ice shelf stability, the detection of glacier phases, the detection of internal water bodies, and also the ice sheet temperature. In this experiment, we focus just on collecting the first sea ice volume signature. We overflew the glacier, the David Glacier, which is the glacier that originates the Drygalski ice tongue, which is the biggest ice tongues in Antarctica. We try to overflow the internal water bodies, and we collect several hours of data over the ice sheet, try to see if we are able to estimate the ice sheet temperature. Also, other objective of the campaign is the analysis of the TB signature by using models and ancillary data, and to demonstrate the concept in the Antarctic environment. Last but not least, also a comparison between the signature of Greenland and Antarctica, because even if we are dealing about ice sheets, they have a slightly different behavior. I mean, for instance, in 2012, the surface of Greenland completely melted. And this has never happened in Antarctica, at least in recent times. So this is just the plot of the flights. We performed 4 flights for a total of 5,000 kilometers. Here we have Zucchelli Station. This is the Drygalski ice tongue, and the McMurdo Station, which is the biggest station of the US, is located something here. So we are very close to the Ross Sea. We performed a couple of flights around Zucchelli Station over the sea and over the end of the ice sheet, and then we went really inside to a Dome Sea. Here we have the Little Dome Sea. We performed this raster, and this is the location of the oldest ice experiment, which is the experiment devoted to study the paleoclimate. We got an extensive ground truth, and we have ground penetrating radar. We have in situ measurement. We have also radio sounding collected during our Italian national program, National Antarctic Program, and also collected from Operation Ice Bridge of the NASA. We have SAR images, and we try to use all of these troves of data just to interpret the measurement that we collected. So for this presentation, I'm going to focus over the ice sheet. These are, here you can see all of the spectrum collected when we flew from the coast to Dome Sea. Going from the coast to the internal part of the plateau, we have the ice temperature, the surface temperature of the ice, which constantly decreasing. At the same time, we have the ice thickness, which increase quite steeply for the first 400 meters, reaching almost 3,300 meters, and then oscillates. What we saw is that the first feature is that the lowest channel at 530 megahertz is pretty flat. Doesn't seem to have any correlation with the surface temperature, and also quite a few with the ice thickness. Instead, we can see that there is a constant decreasing for all of the other channels from 600 megahertz up to 2 gigahertz. And these are well correlated with, with MOS data collected 1.4 gigahertz, and also well correlated to the decrease of the surface temperature. If we look a little bit inside of the data, we can model the internal profile of the ice sheet, which you can find here. Here we have in color the temperature profile of the ice sheet. Here we have the depth inside of the ice, and here we have the distance covered from the coast to Dome Sea. We avoid to show the first 400 kilometers because, as I said, this Robin model is valid only in a steady state. I mean, where the ice sheet is still and doesn't undergo to any stress or movements. Here I show the correlation coefficients that we found between the average temperature of the first 500 meters with all of the channels. What we can see here, which is expected, is that the brightness temperature collected 2 gigahertz has a high correlation with the surface temperature, and this correlation decreases as we go down in frequency. We didn't find any significant correlation to this channel, but if we analyze the correlation with the temperature, with the average temperature at between 1,500 meters and 2,000 meters, we found a better correlation. Anyhow, this correlation study has to be improved in the next months, because obviously it depends on this model, that depends on the thickness, but this is a very assessed measurements. It depends on the surface temperature and also on other geophysical parameters, which is the mean accumulation, and also the conducibility of the snow and the geothermal heat flux. So we want to try to use
Marco,
yes?
to interrupt you, we have 3 minutes.
Okay, we are going to use maybe better parameters than the one that we used up to now. So yes, this is actually the last slide that I want to show. We try to simulate by using the Robin model the brightness temperature that we collected at all of the frequency. Here you show just half of the channels from 500 megahertz to almost 2 gigahertz. What we can see here, first of all, is that there is a good agreement between the model SMOS and also UWB-RAD here. You can see in red is MOS, the observations are in gray, and in black we have the model. So there is a very good agreement at L-band. We have some biases at the other frequency here, but if we going to look at the fluctuations, we can see that there is an agreement also at P-band. So these are very encouraging results, since these are the first measurements collected there, and we are going to investigate deeper this data. The last point, we focused on the Little Dome Sea area. The Little Dome Sea area is characterized by almost homogeneous surface temperature and with a thickness, with a nice thickness, which is more variable. So we try to simulate for all of the acquisition the maximum and minimum internal temperature profile, and with this temperature profile, we try to constrain the data. So what we can see here is that UWB-RAD data are well constrained with these, within this model simulation, and agree also with SMOS. So I finished. And let me spend just 30 seconds to thank the entire team, because this was a really challenging experiment, which involved the team on the field, but also the team that processes the data and interprets the data and use the model. So it was really an effort.
Thank you, Marco, to showing us this nice result of the Antarctic campaign. So let's move on the last presenter of this first part of the cryosphere session, that is Mariam Salim. Mariam Salim will present the snowpack remote sensing using wideband long wavelength microradiometer. So the floor is yours.
Can you see my screen?
Yeah.
Hi everyone, I'm Mariam Salim from the University of Michigan. This is a work in collaboration with the Ohio State University. We are using very long wavelength microwave radiometry to do snowpack remote sensing and derive the snow depth. The methodology is using wideband autocorrelation radiometry. In the upper left figure, we can see the physics of the problem. From the below snowpack, microradiation comes up to the snow layer and go all the way toward the radiometer in the red box. At very long wavelength, the scattering is reducing very fast, and also the rough surface scattering is reducing fast too. Therefore, there is a ray gets reflected from upper surface and bounce off the lower surface and make the first delay ray for the radiometer. Actually, this is a copy of direct ray, which is smaller in terms of amplitude, and it delayed. And here, the delay is the key for us. If we make the correlation of the signal we received in the radiometer, we see a large peak at zero lag, which is the correlation of the direct ray with itself. There is also a lag peak, which is the correlation of the delayed ray with the direct ray. And the time which the second lag occurs is directly related to how deep the snowpack is. The formula in the middle of the slide, this is the method we are finding the snow depth using this time delay. On the top right of the slide, it's our instrument, which is wideband autocorrelation radiometer. It's a traditional radiometer, and in the back end, we have a spectrum analyzer. The spectrum analyzer digitizes the spectrum, and in the post-processing, we perform the inverse Fourier transform to create the autocorrelation function. And we know that using passive radiometer has its own advantages, like it's low power and it's sensitive to the layer structure. In our project, we are using another instrument in the field, which is from the Ohio State University, ultra-wideband software-defined radiometer, UWB-RAD. This instrument is designed to install on the airplane, and here is a smaller copy of that, and we mounted on the boom of our truck. This instrument has considerably has more signal processing structure in it, and it has a conical log spiral antenna to pick up the circular polarization, and also it includes thermal control. It has much better RFI mitigation strategies compared to YBAR. They break up this wideband signal into 12 channels, and each of them is less than 100 megahertz wide. Each channel are digitized, and then digitization is further signal processed to produce the spectrum. They are identifying RFI flags using two methods of pulse detection and subband cortices detection. We want to use this RFI information from UWRAD device to apply it in our own method to derive the autocorrelation function's peak to detect the snow depth. The two systems, YBAR and UWRAD, are mounted on the University of Michigan's boom truck. It's in the right figure. And the experimental setup is deployed at Kinowa Research Center, KRC, at the Upper Peninsula of the Michigan for measurements of seasonal snowpack. Actually, the objective of this experiment is to obtain the evidence of YBAR signal in the seasonal snowpack. The snowpack got at least 58 centimeters deep during winter 2020, which is enough for YBAR signal to be observable. And also from December 31st, 2019 through February 21st, 2020, the air temperature never exceeded 1 centigrade. So there's a good reason to believe that snow was cold and dry enough for the microwave to propagate through the layer. And here in the photograph, we can see the YBAR system on the right side and UWRAD system on the left side of the photo. YBAR has much narrower beam width. Because of that, we are using it as the measurement system for measuring the snowpack itself. And ultra-wideband system has a much wider beam width. And also, they have better RFI detection and mitigation algorithms. So we are using ultra-wideband RFI flags to help us to clean the YBAR signal. On the right, we can see a couple of time series emissivities from YBAR that we used it to match it up with some of the channels of UWRAD radiometer. Channel 6, 7, 8 is here in the figure. And some ground truth measurements, including air temperature and ground temperature during winter 2020. Here in the top left side of the slide, we can see the measured spectrum using YBAR. We have three measurements here, load and cold fed in red and blue curves for calibration purpose, and we have a black one which shows the measured spectrum of the snow. And we can see there is a lot of RFI on it. In the second figure, just next to it, we roughly remove the RFI signal. And in the autocorrelation function figure, we can see the system's initial results, which show that removing RFI does improve the autocorrelation function. And in the blue curve, we can see some peaks compared to the yellow one. So we want to use UWRAD RFI info to detect the ACF peak. Part of the challenge that we had is the frequency mismatch of the YBAR and UWRAD. Because the finest frequency resolution of the YBAR is 200, UWRAD is 250 kilohertz compared to YBAR, which is 200 kilohertz. Therefore, we found some algorithms to map the RFI flags from UWRAD to YBAR. Here, the figure in the left side of the slide shows the RFI signals measured by UWRAD using subband Cortisin's algorithm, the blue noisy curves. So we mapped it to YBAR. And the orange one is showing the power spectrum of the snow measured with YBAR. In the right side of the slide, we can see the autocorrelation function's response. The light blue curve is the result of ACF when we don't have any RFI mitigation. Then we start removing the values which identified as RFI signal from the spectrum for different thresholds. The red curve shows the results of ACF when we remove the most of RFI signal. The figures show that the noise floor is decreasing by increasing the threshold of removing RFI signal. For a 58 centimeter of snow, we expect the ACF peak to be roughly around 3.86 nanosecond, which is not detectable here, and we need more RFI mitigation to find that peak. Here we repeat the same thing for the pulse detection algorithm, and again we can see by decreasing the removing RFI decreases the noise floor. Currently, we are trying to apply all of these methods that I explained here together to derive the peak of autocorrelation function, and we are expecting it to be around 3.86 nanoseconds. To conclude, we performed concurrent measurements over a snow field in KRC at a particular time period of winter 2020 using both UWRAD and YBAR. This work is still in progress, and we are working on removing RFI and decreasing noise floor to extract the snow signal. Thank you for your attention, and if you have questions, I'll be happy to answer.
So thank you, Mariam, for this interesting presentation. Are there any questions from the audience? Also from the chat and YouTube? So no questions. So I propose to stop here. And yeah, to finish here this first part of the session, I would like to thank so much the attendees and also the speaker. And we will have now the coffee break, and the session will continue again at 5 o'clock. So see you later.
Sorry, just an announcement. I remind you that tonight, after the last session, there is the RFI meeting organized by the IEEE Technical Committee on Frequency Allocation on Remote Sensing. So if anyone who wants to attend can go to the MicroRad web page and will find the link to connect to the meeting. So have a nice break.
Okay. Please note that we have to start the pre-session for the second part of the cryosphere session now. Simone, ma te mi senti?
Sì, ti sento, sì, sì, l'audio è buono. Ok, ok. No, funziona, ok, sì, sì.
Non avevo avuto nessuna nessun ritorno.
Funziona assolutamente. Ok, for who are online now and they will present in next session, we can try a test for the microphone and for sharing the presentation. The first is Cesar Condori on list, is online. Hi, Cesar. You are unmute. You can click.
Yes.
Yes, okay. Now your audio is very good.
Perfect.
Okay. And
try to share the video.
Share, right?
Yes.
Should I click share?
Yes, click share.
Yes.
On the right of the options.
So I can share the PowerPoint presentation, right?
We are not okay. Now it's started. Okay, perfect. It's working. Perfect. Okay. Could you try to move the slides only for to be safe? Okay. Okay. It's working very good.
Wonderful. So I will then I will wait here. Do I have to get started now or at 5 o'clock?
No. At 5 o'clock.
Perfect.
Just the pre-session for the preview.
Yeah. Absolutely. Yeah. Thank you. I just wanted to make sure that I'm not missing anything. Oh,
okay. Thank you, Cesar.
Absolutely. Thank you. It's a pleasure to see you. It's a pity we could not make it, but it is what it is.
Okay, now I'm seeing Catherine Vance, who has the second presentation.
Hi.
Hi, Catherine.
Hi, Catherine.
So do you want me to share my presentation?
Yes.
Yes.
Okay. Slideshow. Does that look okay?
Okay.
Yes, good.
Yeah,
yes.
Perfect, perfect, no problem.
Moving. Yes.
Okay, great.
Thank
Should
you
I
very
stop
much.
sharing?
Then the third presentation,
August
Demir, he isn't
here,
online,
yes. He's
but
here.
okay, we'll try next.
Shall I share my screen or?
Yes, share your screen.
Okay, yes.
Okay.
One moment. Yes. Now you can, yes, you can share.
Can you see it now?
Yes.
Yes.
So I'm changing pages. Okay, great.
It's fine.
Okay, perfect. Thank you very much.
Thank you.
The fourth is Xiao Lang Tzu. I don't see her, but and I don't see colleagues. But I see Andreas Colliander. I don't know if you will present in next presentation of your colleague, Andreas Colliander. Can you hear me?
Are you there?
No, I think there isn't in front of the PC.
Okay.
We can try next. Oh, we'll try. Presentation at 6 p.m.
The fifth has also Joel Johnson, but I don't know if
Few minutes ago was online, but now no. I think it was log out during the break. Yes, but it was online very few minutes ago. And I think also for Colliander, Andreas Colliander, because his account is online, but he doesn't reply. And then the last microwave Albano radiometry. I don't find the presentator, but there is also in this case Andreas Colliander and Joel Johnson. So the first, second, and third, okay. The last three, we have Colliander online, but he doesn't answer. So we can try in some minutes. Okay. So it remains only 5 minutes to the second part of the presentation. Andres Colliander, can you hear me? Are you online?
Oh,
Hi. Can you hear me, Andreas? I try to make you a presenter.
Marco is writing to them, to the last three presenters who are not.
Okay.
Okay, we can wait a couple of minutes before starting. And we have 6 presentations, and the first 3 presenters are here. And the last 3, I hope that they will appear soon.
Maybe there is something. No? Maybe Andreas has a problem with video.
Andrea, can you hear us?
Are you talking to me?
Yeah, this unmuted. Okay. Hi, Andreas. I'd like to know if you plan to present one of the papers in this session.
No. Oh, which one?
Okay, perfect.
I didn't know that. Oh.
Because you are one of the co-authors, and I'm not seeing Muhammad Musavi, and so I was asking.
Also Xiaolang Xu for the fourth presentation.
Muhammad should be there for sure. I don't know what's holding him up, but I'll check. He should be there for sure.
Okay.
But then Xiaolan, yeah, if you haven't seen Xiaolan, then she probably won't show up. And unfortunately I don't have a presentation for that. But I'll make sure Muhammad shows up.
Okay, we will see after the third presentation if there is anybody present. Okay, I suppose we can start this second part of the cryosphere session. Welcome, everybody. Good morning, good afternoon, good evening. I don't know where you are, and so every part of the day is valid for this. And this second part of the cryosphere session is spread as the first one over more topics. There are papers about the freeze-thaw status, about the measurements of the estimate of snow depth, sea ice, also snow wetness, and hopefully, if the authors will be present, also electromagnetic models for polar ice sheet. Okay, let's start with the first presentation, which will be carried out by Cesar Congoli. Is an optimal interpretation-based approach to combining passive microwave spaceborne retrievals of snow depth with in situ snow depth measurements.
Thank you, Simonetta. Thank you very much. So I will present a method here of combining satellite-based estimates of snow depth with in situ-based measurements of snow depth. And that method is called optimal interpolation. So the question is, why do we have to blend satellite and in situ snow depth? Now, with satellite here, and I just felt that I have to be more specific. I'm talking about passive microwave satellite measurements. So that is an important thing here. Not any satellite sensor. So first, there are plenty of in situ measurements of snow depth and a very, very long record spanning many decades, right? So actually, the Global Historical Climatology Network, daily run by NOAA, has about 10,000 stations that are capable of measuring snow depth. So it's plenty of snow depth measurements. These measurements have the best absolute accuracy on a very local scale. So the problem is that their distribution is very uneven, and latency is an issue for real-time applications. On the other hand, passive microwave-based satellites have excellent coverage, so that's important, right? Because there are sensors that have limited coverage. So they have excellent coverage and latency, better latency, superior to in situ data. However, passive microwave satellite sensors that up to this day, they have lower absolute accuracy than in situ data. So that's why I wanted to make this specification. Because we're talking about traditional current passive microwave measurements. So why snow depth and not snow water equivalent? Because snow water equivalent is the most important hydrological parameter of snow. Because we lack routine snow water equivalent measurements. So that's the first thing. And the second thing is that SWE, on a large scale basis, can be estimated from snow depth. So snow density is a more conservative property, and there are methods over there. There are very good methods that have been applied with great success to convert snow depth into snow water equivalent. Here I present a graph taken from a paper of Sturm et al. 2010 that shows that 95% of the variation in snow water equivalent is explained by snow depth. But the spread in nonlinearity increases with depth. And the other portion of the variability explained by the snow classes and by the season, right? And here, again, I present here the very elegant parameterization of Sturm et al. That estimates snow density as a function of snow depth, day of year, and a set of parameters specific to these snow classes, right? So that's why we just tackle snow depth first and then SWE later, rather than just attack directly SWE, because we don't have plenty of measurements on the ground. For this project, we have used AMSR2 snow algorithm, so the AMSR2 instrument, to derive snow depth. And we have adopted the NASA algorithm, snow depth and snow water algorithms that are explained in Kelly et al. 2009. So I give the references in the last slide. And so that is the basis for this project, right? And there are different sensors there, SMIS, and other ATMS and other sensors. So we are using M32 as the basis, as the satellite component of our blending approach. And on the left-hand side of the presentation, I show some maps of snow depth. And on the right-hand side, I show the algorithm, the Kelly et al. Algorithm, which is purely microwave-based with dynamic regression coefficients. So it's a statistical algorithm. It's purely based on microwave. And also is based on the channel frequencies 10 gigahertz, 1937 gigahertz. And you can see here in the table that M32 is a follow-on instrument F3. It's pretty much very similar configurations. And SSMI instruments has a larger footprint, so coarser resolution, and also lacks 6.9 and 10.7 gigahertz. Here, I show some results of intersatellite snow water equivalent evaluation. On the left-hand side are maps over the United States of snow water equivalent retrievals based on the M32, so there's just pure satellite evaluations. The middle panel shows you the SWE map based on the ATMS instrument. So the ATMS, it's a different configuration, right? It's a different satellite configuration. And the algorithms to retrieve SWE is different. The approach is different than M32. And then on the right-hand side, you have the ground truth SWE measurements here. And you can see here that there is a significant underestimation of SWE over the Western US, which is mountainous. And also over the Northeast, upper Northeast, which receives significant snow accumulations. So the point of this is to show that even though you have two different passive microwave instruments, different configurations, different algorithms, you have consistency in terms of the bad performance and the good performance. The good performance is in the plain areas limited to SWE less than 200 millimeter, with less forest coverage. So the point of this is that these passive microwave-based retrievals based purely on microwave measurements have limitations that no matter what you do to the algorithms, so different algorithms, no matter if you're a great master, right? If you're a Michelangelo, there is a limit of what you can do. So that's the point of this. And I think in the microwave snow community, I think this is pretty much something that everybody agrees. But this is to show that so the need for combining, for getting other information to improve retrievals. Okay, so that's why we need combination approaches, right, with passive microwave. I'm not saying. So there has been success in active microwave retrievals. We're talking here about using the passive microwave sensors here, which offer great coverage, global coverage, large scale coverage. So one of the methods is what is called two-dimensional optimum interpolation that combines the satellite-based snow depth with in situ-based snow depth, where the satellite is used as first guess. So you use the satellite as first guess, and then you compute a snow depth increment at the analysis point as a weighted average of data increments at the station location. And then the end result of this is here when we use M32, and you can use other instruments, right? A daily 12-kilometer blended snow depth on a global basis. So this is one approach, and there are different approaches. There are Kelvin-based approaches. This is the very simple. It is a simple data assimilation approach where the errors are fixed, error parameters of the scheme are fixed. Another blending approach is the variation data assimilation used in globe snow, and I give the references here. So in the back. So this is a review of two-dimensional optimal interpolation, and I don't want to delve too much into the details, as I mentioned, right? So the idea is to compute a snow depth increment, delta snow depth, right? Where the satellite snow depth is used as Fergus, and that is computed as weighted average. So the challenge is here to compute the weights. And then we compute the weights based on these correlation matrices. Okay? And the most interesting part here is the correlation between snow depths, the autocorrelation, so mu ij, right? So the correlation structure of snow depth is a function of, it's a product of these two functions, alpha and beta, where alpha is an autocorrelation function with respect to distance, horizontal distance, and beta is the autocorrelation function between snow depths, right? Snow depth increments is very important, between snow depth increments, with respect to elevation. So these are taken from Brusnet 199 publication, Journal of Applied Meteorology. So you use a second order regression correlation function for horizontal distance and square exponential correlation function for elevation. So these are to compute the weights, right? An e-folding scale of 800 meter and e-folding scale of 120 kilometer, where the correlation drops to 0.3. So that's the e-folding scale. So these are the most important, interesting things here in the scheme. And we have carried out a extensive evaluation of this and playing around to optimize the scheme. The first thing is, is the satellite value added, right? Because we mentioned that there are major limitations to the satellite retrievals. And we did an experiment. We used optimum interpolation without satellite at all, just using in-situ data and with the satellite. And we found that the satellite estimates, although they have major limitations, right, improve in-situ interpolated snow depth. So they add value. Well, improve. They provide information. So that's the first thing. And the second thing is that these schemes, so again, it is rather easy compared to more sophisticated data assimilation approaches. Right? It improves performance compared to satellite and forecast snow depth. So we compared it with the Global Forecast System, or GFS, especially over mountain terrain. So the major improvements here are achieved in mountain terrain, and probably due to the two-dimensionality of the scheme, so autocorrelation with respect to elevation and to horizontal distance. And another important assessment that we made, we compared this scheme with simpler approaches, such as the Cressman interpolation, what's called inverse distance weight interpolation, and simple averaging. And we found that the
Cesar, we have just 1 minute.
Absolutely, we will get it. So we found that this is much better. And in fact, the Cressman interpolation performs the worst. And these are some statistical assessment results in terms of bias and in terms of root mean square error over low elevation, over high elevation, where it shows that the high elevation microwave is much underestimated snow depth. And also this shows the statistical assessment results of the optimum interpolation compared to this Cressman, compared to other interpolation methods, and it's much superior. So these are the references that I cite in the presentation. So thank you very much for your attention. I think I kept myself within the 10 minutes.
And thank you, Cesar, for your interesting presentation. There is time for one short question.
Sure.
Any question?
Yeah, sure.
Question from the audience? Or from the chat? I don't know if...
Yeah, I don't see chat here. I don't know how to get into the chat. I'm so sorry. I am so backward in terms of this technology.
Okay, but I don't see
But if
any.
you see the chat, if you can convey to me, I would appreciate it.
There is nothing. So thank you again. We can move to the next presentation. Next presentation is a new approach for retrieving sea ice concentration and classifying sea ice type using satellite microwave radiometers. It will be made by Catherine Wentz. Please, Catherine.
Yes. Hi, thank you. Give me 1 second. Yeah, so hi, everybody. I will be presenting on a sea ice retrieval algorithm, both for sea ice concentration and sea ice type. We use microwave emissivities as our basis. My name is Catherine Wentz, and the co-authors are Carl Mears and Frank Wentz, and we are based at Remote Sensing Systems in Santa Rosa, California. Okay, so what is unique about our algorithm is that we use emissivity instead of brightness temperatures as our basis. And we do this to correct for the atmosphere. And so here we use a radiative transfer model produced at RSS. We use the microwave radiances and we calculate TB up, TB down, and transmissivity from INSEP, columnar water vapor, and cloud liquid water content. We also get surface temperature from INSEP. And the past algorithms, such as the NASA team and Bootstrap algorithms, were working primarily in brightness temperatures. In addition, we intercalibrate our brightness temperatures across microwave sensors. And in this way, we won't need tie points. So our aim is to get a 35-year sea ice data set. And in this presentation, I'll be focusing on AMSR2 in particular for our algorithm training and testing. Okay, to start with, let's look at the sea ice concentration algorithm. And so it's relatively simple. We use a linear regression with a combination of emissivity values. We're looking at the microwave radiance from 11 gigahertz to 37 gigahertz in both vertically and horizontally polarization. And then we train the algorithm and we train coefficients and do the dot product between our combination of emissivities to find an ice concentration. And in our second step, we do a seasonal adjustment. And so we simply add a post hoc depending on the day of year and our first guess at sea ice concentration. And so we add the first guess with this post hoc adjustment and we get our final ice concentration value. Our ice classification algorithm is very similar to our concentration algorithm. We're trying to find first year and multi-year ice. So first year ice is ice that has that melts in the summertime, and multi-year ice sticks around for many years. So again, we use a linear combination of emissivities in the same channels. And in this case, we perform a linear discriminant analysis. Now we do this instead of a principal component analysis because the linear discriminant analysis finds the axis of maximum variation between classes. And in this case, it's between the first year ice class and the multi-year ice class. And you can see how that might differ from the principal component analysis, which finds the axis of maximum variation across your entire data set. So we have to do a supervised approach because we are finding classes of data. In our second step, we also use a machine learning technique. Here we are incorporating a multi-year ice climatology on this y-axis. And that is the probability of a grid cell being multi-year ice. And it's largely a correction for in the summertime when we're finding that emissivities of first-year ice and multi-year ice are pretty similar. So we need some help in the summertime. And so what this support vector machine does is it finds this maximum hyperplane of separation between our classes of ice, or multi-year ice and our first-year ice. And we use the vectors that are orthogonal to this hyperplane of separation to find our ice type. So in this case, our feature inputs are the first linear discriminant, the multi-year ice climatology, and then trained coefficients. And if this, if the dot product between those and the trained coefficients plus an offset, if it's less than 0, it's first-year ice, and if it's greater than 0, it's multi-year ice. Okay, so by this time, you might be wondering what data sets are they using to train their algorithm and test the algorithm. As I said before, we're focusing on AMSR2 at the moment. And here I've plotted the emissivity values at 11 gigahertz V-pole and 37 gigahertz V-pole in the right-hand panel. We're using 11 gigahertz. It is, because it's not as sensitive to weather, it's very good at finding sea ice concentration, as you can see from the high emissivity values that are indicative of that 100% sea ice concentration. And then the 37V channel is, although it is affected by weather, it is particularly good at finding multi-year ice. And you can see that in the lower values of emissivity in the middle of the ice region here. So we need to pair this emissivity data with truth data sets. So we're using sea ice concentration from NSIDC, the NASA team algorithm in particular, as well as sea ice age from NSIDC, which characterizes ocean, first-year ice, and multi-year ice. So here is how our algorithm performs, looking at the sea ice concentration product. So I've binned biases for each month in 2018. This is a month separate from our training, or sorry, this is a year separate from our training years. And we are taking the difference between our concentration product and the NSIDC concentration product. So that's a fraction of ice. As you can see, in January, we have biases around negative 0.02, so 2% sea ice concentration, up to in the summertime, we have a bias around 0. So the two algorithms look pretty similar in the summer. And then in the late fall and early winter, we have a bias of around negative 0.04, 4% ice concentration. So we decided next to plot a time series of the total sea ice area for both products. So this time series spans 2013, every day in 2013 up to 2019. We calculate the sea ice area by doing, we take the concentration for each pixel and we multiply it by 25 kilometers squared because it's a polar stereographic grid. And then we sum over the entire Arctic. And as you can see, RSS is in black and SIDC in green. They agree during these summer periods. But then in the late fall, early winter, RSS is biased low. So that's something to investigate further. And another takeaway from this figure is that the sea ice area is indeed declining over time in the summer months. So as we might expect. And this slide shows the sea ice classification algorithm performance. Again, I have binned the the performance by month in 2018. Now, in this case, our metric is the RSS and NSIDC agreement pixels, those total pixels divided by RSS total pixels for a certain ice type. So on the left-hand panel, it's first-year ice, and on the right-hand panel, it's multi-year ice. And zooming in on first-year ice, we see that our algorithm does well, 90% agreement in the months January through May. We see a decline in percent agreement, especially in September and October. And then it goes back up to around 90% agreement. So that's interesting. And even more so interesting is looking at the multi-year ice percent agreement. We see it's lower generally in these January through July months, and that it ranges from 75 to 70%. But in September and October, it goes up. So it's almost doing the opposite thing that our first year ice percent agreement is doing. It's going up instead of down. And so I investigated that further, and what I found is that so if you pay attention to these purple and pink plots at the bottom of the larger panels, that tells us the total number of pixels of first year and multi-year ice. RSS is on the left and SIDC is on the right. So RSS, and multi-year ice is in the pink color, and first year ice is in this bluish purple color. And so for our product, as we might expect, the first year ice declines in the summertime as it melts away and you're left with multi-year ice. The same thing happens with the NSIDC product. However, at a certain point in September, their first year ice, they change it to multi-year ice on one day. All the remaining first year ice becomes multi-year ice. And what that does is it significantly reduces the number of pixels of first year ice. And so that's why we're seeing a drop in percent agreement of that first year ice. And while we have a decrease in first year ice pixels, we have an increase in multi-year ice pixels. And that's why we see an increase in the percent agreement in September. So that was a fun little investigation and definitely something to keep in mind when we do further testing of our algorithm with this product. Okay, so that's it for now. I'll quickly list these conclusions and take questions. So we modeled sea ice concentration and sea ice classification from linear combinations of microwave emissivity derived from intercalibrated microwave radiometer brightness temperatures. We trained and tested our algorithm with NSIDC, sea ice concentration and age data sets, as well as AMSR2 brightness temperatures, which we converted to emissivity with the radiative transfer model. And finally, the RSS sea ice concentration algorithm is lower, -0.01 to -0.04 bias. And then the NSIDC product in the winter months, the RSS sea ice classification algorithm percent agreement is on average greater than 70%, except in summer months when there are very few NSIDC first year ice pixels. So that's it. And thank you. I'll take questions at this time.
Okay, thank you, Catherine. It's a very nice presentation indeed. I don't know if there are questions from the audience or from the chat.
May I make just one comment quick?
Marco, go ahead.
Yes. So when you show slide 8 and 9, I think you show the bias, and it seems that you have the bias just, not just, but okay, like this one. I mean, the bias is higher during this winter. So it seems related to first year ice, because in the summer you don't have any bias or very little. Do you have any idea why you are underestimating the first year ice?
That's a very good question. That's actually the remaining question right now. It could have to do with the fact that we're using emissivity instead of brightness temperatures. And that's a very good point about it being probably due to first year ice because it is in the winter. Honestly, I'm not sure. And I'll have to think about it though in terms of first year ice and why. I've seen on the actual maps that we generally across the Arctic have lower spots of concentration. So maybe just like hone in on one of those spots and investigate further. But thank you. That's a really good question.
Thanks.
Okay, thanks. Any other comments, questions? Okay, we can move to the next one. Is sea ice observation with 0.52 gigahertz microradiometry as part of the Mosaic campaign. And it will be presented by August Demir. I don't know if I correctly pronounced your name. Can you hear me? August?
Sorry, I couldn't unmute myself, so I'll share again. Yeah, okay.
Okay, perfect.
Sorry. So let me start now. Okay, so this presentation is going to be about wideband radiometer that I operated at the Mosaic campaign in order to observe sea ice emissions. And so our motivations to operate such wideband radiometer is to increase the ice thickness retrieval limits because current L-band radiometers can retrieve ice thicknesses up to 1 meter, depending on ice type, of course. And also we are measuring the ice emissions with a wider frequency spectrum with multiple channels. So we hope to improve retrieval models as we are characterizing the sea ice emissions with more information. So Mosaic Expedition is a great opportunity to observe the Arctic sea ice with this instrument, and there's extensive in situ measurements, so we hope to improve our retrieval models. So Mosaic Expedition is basically an ice camp, drifting ice camp in the middle of Arctic. It had 5 legs. I attended the first one and operated the instrument. So in the map, the yellow part shows the first leg of the expedition. I will share data from only that part. Even though the measurements continued in leg 2 in January, that data is still processed. And in leg 3, we had to wrap up the project because the melting season started. So the instrument is a 4-channel version of ultra-wideband radiometer. Basically, the channels are supposed to cover between 0.5 to 2 gigahertz with these frequency channels from 540 to 1740. And each has bandwidth of 88 megahertz, which helps with the RFI detection and mitigation. Again, as mentioned before, maybe, but this instrument performs real-time RFI detection and mitigation developed manner. So it's a ground-based instrument, stationary, and the instrument was put on top of 4 or 5 meters of mast with variable height. The head of the instrument can rotate in elevation and azimuth, so to give us flexibility in sea ice emission measurements. Basically, the antenna was rotated automatically every 15 or 10 minutes to measure the sky, so that it can help with calibrations. The area we observed was flat surface, so it was melt pond, probably no ridging or anything, but the instruments were positioned on a reached location. So in the beginning, the ice thickness was around 70 centimeters or so. So another feature of instrument is that it has spiral antenna with which observes right-hand circular polarization, and the antenna beam width is around 60 degrees. So it gives a antenna footprint around 10 meters to 30 meters elliptical shape. So these are the measurement results. These are calibrated brightness temperatures from all channels. Basically, in the beginning of measurement, like 4 or 5 days, there's significant jumps in the measurements. These are because of the orientation angle of the antenna. I changed it, and as you see, at 50 degrees, brightness temperatures drop. At 45, 40 increases, and in the last 4 or 5 days, I kept it at 35-degree angle. And when I did that, we could observe a gradual increase in the thermal emissions from almost all channels. Here, channel 1 is an exception because there was a significant RFI exposure from instruments computer. So I had to loosen the RFI mitigation limits for this channel only. So in order to understand this, we model the sea ice emissions. We use brine volume estimations from Frankenstein-Garner and first-year and multi-year ice permittivities from Wand et al. And apply the incoherent radiative transfer model to account for multiple reflections. Basically, we model the ice as planar layers of snow, ice, and ocean. There's no volume scattering assumed because we are working on low frequencies, and snow was dry during the campaign, and there's no surface scattering assumed either. So we had extensive in-situ measurements as well from the site. There were deployed digital thermistor chains which measure the ice temperature profile, and with 2 centimeters of resolution vertically. And also there were ice coring activities in a representative site. So on the left figure, you see that the temperature time series of the during the measurements of the instrument, you see that the different depths from the ice temperatures change, and the air temperature is the one that fluctuates most. And you can see the ice surface temperature around -12, and also mid-layer temperature is shown. You see that snow is isolating too much from the air temperature. So these were important to know exactly the ice temperature we are measuring. And also we detected ice growth around 7 to 8, maybe 9 centimeters during this measurement period. Also, ice coring samples show that there is these melt ponds have very low salinity ice, and but at the bottom there is a very high salinity, 5 to 10 centimeters basal layer, and it keeps growing every week. So we thought that adding these additional first-year ice layers would be important in our model. So in order to compare, we applied the sea ice model on the top right. There's 50 centimeters of snow, more or less, during the measurement, and the total ice thickness was around 72 or so, and there were 5 to 6 centimeters ice growth during this time. And as you see, we modeled the ice as secondary ice, upper part of 64 centimeters and bottom ice layer of 7 to 12 centimeters as it grows. So on the time series of brightness temperatures, you see the colorful lines are showing the channel brightness temperatures again, and the green line is just the air temperature. The black lines here are the model estimations. So as you see, model also predicts, if we use this mixed multi-layer sea ice model, the the model also estimates that there's an ice growth, and there is also good agreement between what we measured and what we estimate. And if you look at the scatter plot, there's also very close data points to unity line. The only problem with is the 540 megahertz channel. Again, the bias is good, but precision is bad. It's, again, as I mentioned, it was very bad, badly affected by computer RFI. And also I applied this model for other observation angles from top to bottom, 40 degrees, 45 and 50 degrees observation angles. And to better understand, if you look at the scatter plots, corresponding scatter plots, mostly they are doing a great job. The measured and model are in good agreement. Channel 1 again is problematic. Sometimes channel 4 and channel 2 are doing jumps, but these are unexpected, and as I figured out, they're originating from the instrument itself sometimes, but later this time the instrument keeps operating stable. So in conclusion, it was a successful measurement during the Mosaic expedition. We had a good match between wideband measurements and formal estimations. Most importantly, we understood that the basal first-year ice layer is important to model the emissions, and our instrument was able to detect the winter ice growth during this time, thanks to in-situ measurements by other groups in the expedition. So thanks for listening.
Okay, thank you very much. Very good experiments, a nice new sensor.
Thank you.
Any questions, curiosity, comments from audience? I didn't see anything in chat.
Simonetta, can I ask just a question to August? You collect a lot of remote sensing data during the experiment, and it was really quite an effort. I was wondering, do you think that now or later will be possible to analyze together all the remote sensing data? Because this could be useful also for your modeling. Just to constrain better the modeling phase.
Yeah, we can use that for sure.
Is it? Do you have a time frame? Where do you expect that all of the other scientists put online in the Mosaic database their data, or it's impossible to foresee?
For people, if these data will be used outside Mosaic expedition participants, non-Mosaic projects, then it should be around 2023 or something. The data will be published publicly. So, unless they decide to publish, I don't know. We need to get their consent, I believe, but I don't know. The uploading to Punji repository still continues, and it may take time, around 3 to 4 months still, because the expedition ended just a few months ago.
Okay, thanks a lot.
Okay, yeah. There is also a question in chat. As a curiosity, the radiometers was installed in Svalbard also, or?
Sorry, I couldn't catch the question. Installed where?
Svalbard Islands.
No, the instruments were just on the ice floe only, and some were on the ship next to the ice floe. Ice floe was drifting in the middle of Arctic all the way down to Svalbard. So. Mm-hmm. Yeah.
Okay, thank you again. Let's move to the fourth presentation. Is global freeze thaw data records using spaceborne L-band radiometers. And the presenter is Xiaolan Xu. Probably is not the correct pronounce.
Yeah, it is. It's very close.
Sorry for that.
Okay, I'm sharing my screen now. Can you see it?
Yes, we can see it.
Okay, great. Hello, everyone. My name is Xiaolan Xu from Jet Propulsion Lab. Today, my topic is global freeze-off data records using spaceborne L-band radiometers. So first, I would like to thank my co-authors, Andres Kalenda, also from JPL, and the other two, Kimo Rashmina, Tiamo Manders from Finnish Meteorology Institute. So this is the outline of the presentation. First, I will talk about the synergy between SMOS and SMAP freeze-off product development. So currently, the L-band radiometer on orbit is SMOS and SMAP, and both of them have the freeze-off product. So there are a lot of synergy between those two. Earlier in the session, Kimo already gave a presentation about the detailed development of the SMOS. So in my presentation, I will focusing a little bit more on the detail of the SMAP algorithm and more on the comparison between those two. So I will, after the summary of the SMAP algorithm, I will talk more detail about how two products have some differences in the data processing development. After that, I will give a preliminary result of the comparison between those two. Finally, I will give a summary. So this is the milestone for the passive freeze-off product development separately for SMAP and SMOS. Freeze-off product has been included in the requirement at the beginning of the SMAP, but using active input. When the SMAP active stop working, we switch the input from active to passive and continue the development for the freeze-off. So then currently the freeze-off product is based on the brightness temperature input, and the data can be downloaded from the NIS IDC. And this is the current version, which include both polar grid and the global grid in two different resolution, 9 kilometer and 36 kilometer. And for SMOS, since it's launched earlier, so it actually have a longer development period. And up till this June, SMOS also public the official freeze-off product, and also it can be downloaded from the FMI and the ESA server. So for the SMOS freeze-off product, it's in the North Polar Grid and it is in the 25 kilometer. So there are slightly different resolution and also coverage for both products. And for comparison, in my presentation, I was using North Polar product from both products. And for SMAP, I was using 36 and SMOS is 25 kilometer. So that they are very close in resolution. So this is the flowchart for the SMAP freeze-off algorithm. So basically, freeze-off algorithm is a level 3 product, and it takes the input from the level 1 brightness temperature for both vertical and horizontal. And the main algorithm that we're using is based on the polarization ratio. So after we go through the algorithm, there is a mitigation process. I will talk a little bit more in detail later, but it is MSR weekly mask. And then finally, we'll give the product in North Polar Grid and the global grid. So for SMAP, the freeze-off has a requirement of 80% accuracy. And the way we validate is using the so-called core sets validation. So this is where the core sets are located. And from the in situ, we will have soil temperature and air temperature. So the freeze-off product will directly compare to the soil temperature and air temperature to obtain the accuracy. So over the 5 years, the freeze-out product from SMAP is pretty stable and can be achieved that requirement of 80%. So that's how SMAP validates the freeze-out product. And if we go back to the baseline algorithm, basically SMAP and SMOS share a very similar baseline algorithm. They are all using the normalized polarization ratio, basically take advantage of the differences between vertical and horizontal brightness temperature difference. And after we derive that NPR value, it will go through a seasonal threshold method so that each of the new requirement will compare to the freeze and thaw reference that derive from the previous data. And after we set up a threshold, we can calculate the freeze thaw for each new record. So basically, the freeze thaw can be determined by comparing to the threshold. So the main differences between SMAP and SMOS is the way that we generate the reference and determine the threshold. For SMAP, it is a fixed incident angle, so all the TB is in 40 degree. There's no angle correction in the process. So the thaw reference and freeze reference for SMAP is updated yearly, so that for every year there's a separate freeze thaw reference being generated, and then the final reference that being used in the algorithm will take an average for the previous years. And for the thaw reference, it's using the average of 2 months. And for the freezing reference, it's using the lowest 20 numbers. And there are also a limitation for the SMAP that it calculates the thaw reference and the freeze reference difference and make sure that the difference need to be large enough to operate this threshold method. Well, in SMOS, it actually using all data to formulate the freeze and thaw reference. So first of all, SMOS have different incidence angle inputs. And for the freeze thaw product, they are using 50 to 55 degree incidence angle. So there will be a slightly difference between the SMAP 40 incidence angle. And in terms of the reference, they are using the 50 most extremes value from collected from all the data and take the median value to have the reference for freeze thaw. So you can see SMOS takes more extremes numbers to make sure that they have enough reference difference to operate the reference the baseline algorithm. While SMAP, since the incidence angle is pretty consistent, so it adapt a different way of doing that. So let's take a look. So this is the reference comparison for the thaw reference. Since SMAP is using the average, while SMOS is using the extreme, so you can see the purple and green are the SMOS reference are consistently higher than the SMAP reference. But you can see the x-axis is being into different land cover. Although the number is consistently high, but if you go over all the land cover types, it's pretty consistent. So you can see the difference is consistent over the globe. And the other thing is here I put 3 years of SMAP reference here. And you can see the reference for SMAP is also pretty consistent over the time. The next one is the comparison of the freezing reference. Since for the freezing reference, both algorithms using kind of the lowest point, so we are seeing less differences between the freezing reference. They are pretty consistent. So other than the freeze and thaw reference differences, there are some other other differences between the processing. So the so due to the mission itself, the temporal resolution is slightly different. The data product is all daily updated, but SMAP is combined about like 2 or 3 days of delay. While SMOS, due to the RFI issue and coverage, they are using a 20-day average. The reference, as I just mentioned, SMAP is yearly updated, and SMOS is used the entire data set to form the reference. For the threshold, this is more like a best fit parameter. For SMAP, it is using 0.5, and for SMOS is 0.7. The last differences between those two is the way that mitigates the false flag. In the SMAP, we're using MSAR and the GML climatology weekly mask, and for SMOS is a seasonal mask. I will go a little detail in this too. For the SMAP, we are using the previous MSAR data and also the GML air temperature data to form a weekly mask. So basically, this is a static mask that's generated weekly, so that can help the algorithm to determine which season we're in. But this is a static mask. While in the SMOS, they are directly using the air temperature derived from the ECMF WF, and this is a dynamic input and also the snow cover data. So they also form an algorithm to determine which for each of the record which season are in, and then eliminates the potential false flag. So there are some differences in the false flag mitigation. Okay, so let's take a look how the product compare with each other. Because the different resolution and the temporal coverage, instead of comparing the daily freeze-thaw map, here I'm showing first freezing day for 2016 as an example of comparison. So basically, this tells us when for each of the places start entering the freezing season. So the first freezing day in this plot is defined as 5-day consistent freezing. That means for each of the pixel, it's detected to be frozen. And keep frozen for the next 5 days. So you can see sorry. Although although the SMAP and SMOS shows shows different freezing date, but globally you can see the pattern are very similar in the area where they start to freezing, and overall SMAP shows slightly early freezing than the SMOS. So this plot I was showing the first thawing day, and for the thawing day, the definition is need to be carefully defined because the L band is sensitive to snow melting. So the thawing may not necessarily corresponding to the soil thawing. So it's more close to the snow melting. Same thing, you can see the global pattern are very similar, despite there are also there are a lot of differences in the data processing procedure. Okay, so for the regional comparison, we just pick up some of the region so that we can have a time.
1 minute. You have
this is the last one. So This is the regional comparison, and you can see there are very close results between SMAP and the SMOS. So this is my summary. So in this presentation, we talk about the SMAP freezer product, and it's pretty stable for the last 5 years. And by most metrics, the SMAP baseline requirement is met. The algorithm processing is compared between SMAP and SMOS. So we can see in the global pattern, we have very similar global pattern of the first freezing day and first thawing day. That shows they are pretty consistent for both L-band product. And in the future, we'll have more detailed comparison in different regions. Thank you.
Okay, thank you, Helen. The presentation was really nice, and it's interesting the comparison between these two long life satellites, especially SMOS. And there is any question from persons, from attending people? No, chat, no, doesn't seem to be any question. So thank you again. We can move to the other presentation. This time is a coherent reflectivity model for layered media over an homogeneous half space for combined active and passive microwave remote sensing of polarized sheet subsurface temperatures. Is presented by Aokui Su from the University of Michigan. Is it correct?
Yeah. You got my name correct. And can you see my sharing now? What? Hello?
Yeah.
Yeah.
I can hear you and I can see your screen. So put it in presentation mode and we can start.
Okay. So hello everyone. I'm Haokui Xu from University of Michigan, and my presentation today is a coherent reflectivity model for a later medium over a inhomogeneous subspace. And this model is developed for the idea for the combined active and passive remote sensing for polar ice sheet subsurface temperature profiles. And basically it's for Greenland and Antarctic. We use the multi-channel radiometer to sense the brightness temperature of polar ice sheet, and we have experienced several missions. And the basic scientific goal is we want to find the ice sheet temperature profile, and also want to know the sea surface salinity in polar regions, and also the sea ice thickness. Previously, we used a radiometer only sensing method, and we used a ultra wideband software defined microwave radiometer. In short, is UWRAD. It is working from 0.5 to 2 gigahertz with 12 channels within, and it's observing at 0 degrees. So we have a nearly idea is to combine the radiometer with a radar to enhance the sensing ability. And I will explain why we need a radar in the next slide. So in the right side here is actually a structure of an ice. The penetration depth of microwave decreases as the frequency increases. So if we have different channels, different channels working at different frequency, we will they will receive the emission cumulatively from different depths of the polar ice. And you can see that for the polar ice, it can be decomposed into two parts, and which is the top layer part, which has many layers of density fluctuations, and the iceball part, which is actually very smooth. And here actually shows an example of the ice sheet density profile, and basically it's for most of part of the density part of the ice sheet the density is very smooth. But for the top regions within the top 50 meters, where you can see a lot of density fluctuations. Those fluctuations would modulate the. And so if we want to retrieve the temperature profile exactly, we need to include the density fluctuation parameters. So previously, when we in our UV missions, we need to include the boreholes for the top region density fluctuation region information. However, if we have a radar measurement, we can infer the effects of the top regions from the radar measurement, and then we can extend our flight into regions that do not have a borehole. So here is actually the forward model we previously used for the passive only missions. So we basically divide the ice sheet into multiple layers, and because of the density fluctuations in the top part in our model, we need to use Monte Carlo method to generate a lot of profile for the top reflectively to smooth out the fluctuations in brightness temperature, and then we do the retrieval with the model results and the data. The problem with this model is that because we need to use the Monte Carlo method, and that would take a long time for a single to generate a data cube for the retrieval. And we have this combined active and passive method. In the active problem, we are using a radar to do a measurement for the ice sheet, and for the passive, it's just like previously we used the multi channels to receive the emission from the ice sheet. And so here is actually how we're gonna use the radar measurement. Basically, the radar is actually using a wideband imaging radar, which is actually doing the sounding for the ice sheet. And because the top layer has many fluctuations, and the bottom and the main body of the ice is relatively smooth in the density, so we will mainly observe the radar reflection peaks in the data from the top region. So we just take out the radar sounding data, where truncate that to take the part where the reflection is strong, and we just neglected the part where the reflection is not obvious, and then we use a deconvolution method to process this part of the data to get the reflectivity as a function of frequency. And for the passive part, we consider the top region as having a constant physical temperature, because it is very thin compared to the whole ice sheet, and it can be characterized by the transmission coefficient and reflectivity, the transmissivity and the reflectivity of this cap region. So the overall brightness temperature from the ice body is given in this equation. So the first part accounts for the cap emission, and the bottom part accounts for the emission from the main body, the main part of the ice sheet. And because that the ice is usually low loss, so the absorption is also small. So usually we can ignore the first part because this contribution is very small. And here we do a numerical simulation to validate our idea for the active and passive part. So we use a Gaussian process to generate the density, to generate the fluctuation density profile, and use a exponential function to represent the mean profile of the density. And for the temperature profile, we use a Rubin model to generate the temperature profile, and this is taken from the parameter of the Greenland borehole. So let's look at the active measurement first. So to the left is a simulated radar echo for one profile of the density fluctuation. So you can see that we can see many echoes at the first, and then it actually go to very low when they are corresponding the deeper part of the ice sheet. So with this part which the echo is obvious is from the cap regions where the density fluctuation is obvious. So we take this part and do the deconvolution. And here the right hand side is the reflectivity we retrieved from the radar echo with a 1,000 realization average to smooth out the fluctuation. And the blue circles are the direct model prediction from of the reflectivity for the top region. So we can see that these two results are to deconvolute the radar echo to retrieve the reflectivity is doable. And here is actually the brightness temperature we simulated with our passive method, and the reflectivity of this model, the top region reflectivity of this model is from the previous simulation. So this is actually the direct simulation with the include the effect of the top layer density fluctuations. And this is the reflectivity we have for the top regions. And we put the example of 1,000 realizations and 1 realizations together. And so the most important part is we want to remove the effects of the top region. So we divide the simulation result TB from this figure with 1 minus R cap, which is the R cap is from this figure here, to get a corrected brightness temperature as a function of frequency. So this, which gives us a figure like here. So we can see that even the results for 1 realization and 1,000 realization, they are pretty much the same. So this actually shows that with the radar measurement, we don't need to depend on the Monte Carlo simulation to smooth out the curve, and we can actually get rid of the dependence of density fluctuation knowledge by using the radar measurement. So here are the conclusions. In the combined active and passive method, we use an active radar to measure the cap layer reflectivity, and we use a radiometer to measure the brightness temperature of the function of frequency from multiple channels, and we use the radar measurement to reduce the cap layer effects, and it actually can enhance the retrievability of ice stream temperature profiles. Thank you.
Okay, thank you very much. And any question from persons, audience? I don't see any comments from the chat. Okay, thank you again for the nice presentation. I suppose that we can conclude here this second session on the cryosphere. And thank you to all participants.
Moneta, sorry, so there is another presentation of
okay, I'm sorry. I'm sorry. Okay, last but not least, the last speaker is Mohammad Mousavi and he will present a new snow wetness retrieval algorithm in detect Greenland ice sheet surface melting using SMAP microwave band radiometry. Sorry for that.
No problem. Sure.
You guys can hear me, right?
Okay, sure. Go ahead.
Okay. Okay, thanks for introducing my presentation. So in this presentation, I'm going to talk about a new snow wetness retrieval algorithm that we developed in order to detect the Greenland ice sheet snow wetness, or we can do it on Antarctica, but in here I'm going to talk about the Greenland using SMAP microwave L-band radiometry. So my name is Mohammed Mustabi. I'm from JPL. And my co-authors are Andreas Colliander, also from JPL. And the list of the other co-authors are in here. Daran Takhavi, Joe Johnson, Julie Miller, Christopher Schumann, and John Kimball from University of Montana. Okay, so as an outline for this presentation, first I'm going to talk about the introduction, that why we are doing this thing, and also in one slide that what is our approach. And then I'm going to talk about the ice detection algorithm that we have. Two, which is one of them is the empirical algorithm, and the other one is the model-based, that we call it a SNOR, as a snow wetness retrieval algorithm. And then at the end, I'm going to show you the results from each of the algorithm, and at the end, we're going to conclude with some conclusions. So let's start with the introduction, and as an executive summary, the objective in here, as I mentioned, we want to basically remotely detect the surface melt events over Greenland ice sheet using SMAP L-band microradiometry. The method that we have is by comparing the daily polarization ratio, or NPR, of the measured brightness temperature with a reference value that we usually use the winter conditions for that reference value. The benefits of this technique, all of them comes from its name. It's a passive microwave, as we know, so it's low power, low cost, and it also can operate in all weather conditions. And the other thing is that SMAP is still operational, the microwave radiometer, since the launch time in 2015. An overview of the SMAP, the SMAP satellite, that you all may know of it, but I'm going to read that as I mentioned, it started from 2015 when the launch time was, and the science production was from March 31st of 2015. There are two brightness temperatures of the V pole and H pole. The measurement have about like 30 to 40 kilometer resolution. And in here, we gridded the data on a 9 kilometer polar equal area projection grid for basically in this study in here. So the satellite has a sun-synchronous 6 a.m., 6 p.m. equator crossing orbit with a constant incident angle of 40 degrees and a SWOT width of approximately about 1,000 kilometers. So all of these things helps us to cover the Greenland 2 times per day, one in the AM overpass and one in the PM overpass. And the radiometric resolution of this map is about half a Kelvin. So let's talk about that, why we want to do this, why we want to basically look at the Greenland ice sheet using this map, what's going on and what's the motivation. The motivation in here is that the Greenland ice sheet basically is really important, first of all, for the ice sheet mass balance and also energy balance, as well as the global and Arctic climates. But there's lots of strong melt events happen in the past. For example, there was, as you can see in 2019 in here, there was like a huge melt event, which is one of the recent one that happened over the Greenland. And so the melting can also rise the sea level, which is about like 7%. They can have a contribution of 7% to the current sea level rise from the ice sheets. So because of all of these things, that the melting is going on in the Greenland, and also it is really important for the climate and the mass balance of the ice sheet. So we need to monitor the changes over the Greenland. So in the past studies, they used the higher frequency of 19 and 37 gigahertz from other satellite sensors, such as SMMR. In the new approach, we are going to change the focus on the lower frequency using the SMAP radiometry, because we believe that it gives us more comprehensive information about the ice sheets. So based on these measurements, we developed two algorithms of empirical and model-based algorithm. So let's start with the empirical algorithm. So if you look at the NPR over the Greenland, so it changes in either direction, so it either increase or decrease. So we have to look at the first what happens in the freeze condition in the freeze season. So NPR is usually high in the active melt zone of the ice sheet because of the internal structures that we have over there. but it is low in the dry snow zone or ablation zones because there's less structures, always like at the same like frozen conditions, so there's less vertical structure over there. But during the melt season, when we hit the melt season, so when the melt start happening, there's a layer of polarization happen. It basically creates a layer of polarization difference over the ice that we have, and also attenuates the signals from the deeper layers. Because of this, so the MPR decreases in the dry snow zone because it adds basically a layer of a structure in the vertical layer, and also decreases the MPR in the active melt zone. For example, you can see in here on the left, we have the MPR winter reference over Greenland from April 1st to April 6th. And if you look at the max difference over the whole melt season of 2019, for example, you can notice that there is a different change in the direction of the MPR. As you can notice, for example, in the middle of the Antarctica, where you have always dry snow zone, so there's an increase in the MPR. But on the coast, usually you have the decrease because they are considered as active melt zones. So that's the whole idea, that we want to look at the MPR change, and it gives us basically what happened in the ice sheets. So as I mentioned, we want to look at the change of the MPR. So we use these two conditions of the M1 and M2, which is basically the binary states of 0 or 1. And if it satisfies the condition that the daily NPR increases above the MPR winter reference with some threshold value, as well as the same thing for the TBV, the dipole brightness temperature, we can call that pixel in the footprint of the antenna as a basically melt pixel. So these two has to satisfy with each other. So it's like a AND operation. And you can see there's a logic truth table I put in here that both of these conditions should satisfy in order to consider the pixel as a melt pixel. And the Z parameter in here, it comes from the fact that it basically determines the false alarm rate in here. So I'm not going through the details of that, but I have the details in our paper that is going to be published soon. But that parameter in here basically determines the false alarm rate. And our proposed value is about like 5 for the MPR, 10 for the TBV, which makes this threshold value of like 0.01 for the MPR and about like 9 kelvins for the TBV. The other approach that we have was the model-based. We call it the SNOR algorithm as a snow wetness retrieval algorithm. So in here, we have the brightness temperature from two different models. And by comparing the values of the measured brightness temperature of the SMAP with basically with the different values over the range of the parameters that we have from these models, then we can make a lookup tables, and by looking at them, we can find basically a snow wetness for each conditions. But at the beginning of this algorithm, we have to separate the pixels to be the decrease of the MPR and the increase of the MPR, that we use the same basically threshold as I use for the empirical algorithm, just without the absolute values, to look at the direction of the change of the MPR. Once we have done that, then we go in each of them. So each path are similar. The difference is that we are doing like a different models of the increase or the decrease. And by comparing them, we can find the snow wetness. So let's look at the results that, what are the results that come up from different algorithms that we have. So first of all, the ice mask that we use for Antarctica, I put the reference in here, the ice mask that we use. And that's how it looks like over the Greenland. So they're part of, for example, the coast that doesn't like with this ice mask doesn't come up to the picture, but it's mostly captured all of the Greenland in here. So for the empirical algorithm, we can, using that threshold algorithm for each day over each pixel, we can find the number of melt days for each melt season, which is basically each calendar year, because we're in the northern hemisphere. So as you can notice that the recent melt, the recent basically year 2019, we have the most the most extensive melt events in terms of the area, that there's like lots of melt happening, even though it's really like 1 to 2 days, but that happen in the dry snow zone and never happened before. But for example, in the other years, we may have more number of melt days, but this year is the most extensive one. If we go and just put the number of, like, say, the melt evolution for each year from like May till October for each different calendar year, you can notice that in 2019, at the end of the July, basically early August, so you'll see a peak that comes up, a really strong peak, which considers for that melt events that happen in the middle of the Greenland. That's what happened during the summertime, which is the 2019. So it's a really most recent and most extensive melt event happened over in Greenland. Using our SNOR algorithm to basically detect the snow wetness or measure the snow wetness using that algorithm, you can notice that first of all, we have the same extent for the melt over Antarctica because both of the algorithm uses the same threshold to find basically the pixels that went over the melt in the melt season. And you can notice that we have a different basically percentage of the melt that usually is higher along the coast, and also in this area of the 2019, the middle one, you can notice that it's a really small amount of the snow wetness because it happens only for 1 to 2 days. After that, it's back to the freezing conditions. So the better way to look at this is just if I put it in the bar chart, you can compare the empirical algorithm with the SNOR algorithm, and you can notice that that the 2019 was the most extensive melt year. That there's about like 68% of the Antarctica went under the melt conditions, even though not all of them had the same basically number of melt days, but 68% of the Greenland went over the melt. And the other thing that you can notice that the most intensive one was the 2015, both in terms of the median of the number of melt days, which is about like 25 days from the empirical algorithm, and also median of the snow wetness over the Greenland, which is like 0.35%. So by this, basically I showed the potential of the SMAP radiometer to detect the melt event over the Greenland using basically the V pole and H pole measured brightness temperature. So that concludes my presentation. Any questions?
Simonetta, your microphone is on mute.
Okay, thank you very much for your very nice presentation. Sorry again for having forgotten you.
No, that's no problem.
Okay, I suppose any question from anybody?
I've got a question. If anyone, it's
okay, Giovanni, go ahead. Okay,
just two questions. First, if you validate somehow your results, because validation there is difficult, and the second is if you select a fixed threshold value or not. I'm not understood, and how you select the threshold that you use in your algorithm.
Okay, great questions. So let me back to the slide. So yes, yeah, I have to say yes to both of your questions. Yes, we validated our results with the other algorithms or other papers, but I didn't include it in here. I mean, in our paper, let me just see if I can share it in here too. Actually, I don't have it in here to share because I have to stop sharing again and share it. I don't remember. Wait a second. Let me reshare my whole screen. Wait a second. Okay, so in our paper that it's basically going to be published soon, I'm just showing in here. So yes, we validated, for example, on the left, this is for example, this is for Antarctica, for example, that we show that with the other measurements from the different sensors of the SSMR and the SSMI, we validated that one for the Greenland, from the Antarctica, but for the Greenland, because we recently applied the algorithm to the Greenland. We haven't like compared it to the to basically the other measurements, but we're planning to do that as a comparison to make sure that it's working. The second question that you have in terms of like a threshold that we use, so the threshold that we have for the NPR, the Z parameters, I'm assuming that was your question. And for that one, we basically use these conditions that we have to satisfy the number of, to satisfy these two equations, that what is the minimum Z that we need. Actually, we did that in our paper. If I go back in here, we have so in order to show that what is the right parameter, so we basically use these two conditions to come up with a number of reference state that we need for different Z parameters. Then we plot these two together, and you can see that there's a region that you can go and pick the right value of the Z parameter depending on the number of reference state that you're using. For example, in the presentation that we have in here, I use we use like about 5 days or 6 days of the reference days, and these values of the NPR Z parameters of 5 and 10 would be enough to satisfy these two equations. Did I answer you? Did I answer your questions?
Yeah, yes, I will go to the paper when it will be published.
So this paper is published. Like it's going to be
okay.
It's going to be out soon. It's in the it's in the Cryosphere journal, so it should be out for the interactive review things online. Should be soon, I guess.
Okay, thank you very much. Any other questions? No, if so, we can conclude this interesting session on cryosphere. Thanks to all, to audience, speakers, participants, and so on. And see you in next days, I suppose.
We have just a notice. I mean, a notice and advertise from Paolo De Matteis about the upcoming RFI discussion.
Thank you, Emanuele. I have just this announcement. The frequency allocation remote sensing technical meeting is organizing this RFI discussion starting in a few minutes, just to give some time for everyone to join. If anyone who is in this session wants to join, still has a few minutes. We are going to cover two topics. Dr. Ashley Zauder is going to introduce the plans for National Science Foundation's Spectrum initiative for wireless spectrum research, and we'll have a question and answer discussion after that, and then the technical committee is going to introduce its proposal to develop standards related to RFI impact and quality band evaluation. Participation is open to anyone. In order to join, please use the link that is posted on the MicroRad webpage and also been shared by email with all the technical committee members. So we'll start in a couple of minutes just to give time to everyone to join. So I hope to see you there, and I also would like to thank again the organizers of MicroRad to give us this opportunity to have this discussion. Thank you, Simonetta, Marco, Emanuele, and everybody else.
Thank you, Paolo, and enjoy the meeting and have a good meeting on RFI problems.
All right, thank you.
Okay, bye-bye.
Okay, bye-bye. See you tomorrow.
Bye-bye, everybody.